Hello students, welcome to the IMS GATE Academy. How are you all? Everything is good? Please let me know and confirm once whether all things are fine or not. That my Saurav Upadhyay. Good evening, Saurav. So please confirm whether all things are good or not. I hope all are good. So as you know that we had started, means a couple day back we have started our all is fine, excellent. So we had started our YouTube series, that is quick revision through formulas, and in that most of the subject belongings to your electrical, IN and AC, civil and mechanical, and means most of the subject, most of the stream that has already been completed. So moving ahead with the series of the electrical as well as IN, you can say that this session will going to deal with the formulas, which is basically belongs to the one of the very important subject, or you can highly weighted subject of the electrical stream, and as well as for the IN stream to some extent. So, and the subject is, yes, definitely the subject here is electrical machine. And I know most of the students are looking for the formula revision of the electrical machine only. All right, so before entering into this session, please let me give you a brief info about the session that I have already taken. On the 16th of Jan, I have taken the measurement subject, in which I have written and I have given all the formulas which are very, very important considering to the GATE exam. Means if you go through those sessions, definitely you will going to crack each and every question of the GATE exam related to your measurement subject. So guys, this is my humble request to please mark your attendance by hitting the like button, and also inform your friends and colleagues so that they can join the live, as well as we are going to have a great and excellent session of the electrical machine. All right, so definitely we will going to conduct this session in a best manner as much as possible. All right, so please inform the student and share the link in your community. Okay, रुपेश कुमार ग्रुप कैरेक्टरिस्टिक का फॉर्मूला भी बता देना. अरे टेंशन ना लो, सब बता दिया जाएगा. ठीक, please inform the students and your friend and your colleagues so that they can join, and we will going to have a wonderful session over here. All right, so shall we start? So basically in the part 1, means in the first session we will going to see the formula related to the chapter transformer and the induction machine, and after that we will be going to having a little span of break, and after that we will going to start the two chapter, that is DC machine and the synchronous machine. All right, so please share the session link so that most of the student will get a benefit out of this. All right, so shall we start? बिल्कुल एनर्जी नहीं दिख रही मुझे. Shall we start? All right, चलो. This is the transformer. तो इंडक्शन मशीन भी आज ही होगा. हाँ, आज पूरा होगा. आज इलेक्ट्रिकल मशीन पूरा रिवीजन हम लोग यहाँ पे करने वाले हैं फॉर्मूलाज का, तो उसके लिए टेंशन लेने की जरूरत नहीं है. ऑलराइट, सो this is a transformer, which is a basically chapter 1, and this belongs to EE and IN stream both, and the weightage for the EE is between 2 to 4 marks, and for the IN stream it is varying between 1 to 2 marks. All right, and these are the important topics. If you go through the past year question, or you can say the PYQ, you will going to see that in the transformer most of the questions have came from this topic, that is iron losses and copper losses, open circuit and short circuit test, voltage regulation and efficiency. All right, so let us start. So this is the introduction part. So where the transformer is a static device, and in which we have a stationary part. All right, and those two windings are interlinked by a magnetic coupling. All right, so there are no interconnection of the electrical. Whatever power is transferring, they are transferring through the magnetic domain. All right. Now, your transformer is a constant frequency and a constant flux device. And remember one thing, that the principle behind the transformer action is Faraday's laws of electromagnetic induction. And the last is that the transformer is a constant frequency and constant power or flux device, you can say. So this is a transformer. This is a transformer in which this part is known as a primary, where the source is connected, and the remaining part, or you can say the other part of the transformer is referred as a secondary or the load side. So at the primary we will apply, or we will give a supply voltage, and at the secondary side we will going to connect the load. So here V1 is the supply voltage, I1 is the current which is flowing through the primary winding. This is the primary winding, and due to this current a flux will going to be happen, and this flux will leak this secondary winding, and this flux will going to create the current I2, and this I2 is basically known as the secondary side current, or you can say the load current. Alright, so basic principle is that the Faraday's laws of electromagnetic induction. Anyway, we are not about to discuss all things here, because this series is basically related to the formula things. Alright, so let us start with the formula. The step-up transformer is a transformer where number of primary turns is less than the number of secondary turns. This turn N1 is less than N2, and the step-down transformer means the voltage is decreasing when we moving from primary to the secondary. So N1 is greater than N2. Now see here, EMF per turn in primary equal to EMF per turn in secondary. So what do you mean by this? EMF, which is E1 by N1, is equal to secondary EMF is what? E2 divided by N2. Next, compensating primary MMF. Is it clear, Rupesh, Saurav? All? Compensating primary MMF and secondary MMF. So primary MMF is number of turns of the primary and current entering into the primary winding, which is I1 dash. Please do not write I1 here, because I1 is what? This I1 is a source current, and we need to write here the current which is entering into the winding. That is the primary winding. And here secondary turn is N2, and the current here is I2. Basically this current, not this current. Here the current I1 dash will going to enter, and this is I2. Alright everybody. Next, primary volt ampere. So here V1 I1, that is the supply voltage, is equal to, the supply volt ampere is equal to secondary or load volt ampere. Done. Next point is instantaneous power input into the primary is equal to instantaneous power output from the secondary. So ideal transformer. What is ideal transformer over here? The transformer core has infinite permeability. So if the core is having the infinite permeability, then it is known as ideal transformer. So the flux established without any magnetizing current. So without any extra current, we can transfer the power from one side to another side. The primary and the secondary winding have zero resistance, so there is zero ohmic losses. So this is ideal transformer. The third point is there is no magnetic leakage flux. Third point is that, and the fourth point is core loss considered to be zero. What is core loss? Everybody please let me know in the chat box. And the last one is BH curve. This is curve is linear. Please let me know what do you mean by core loss, or what losses consisting of the core loss. Next, this is the equivalent circuit of your transformer, where this side is referred as a primary side, and this side is referred as secondary side. Okay, so please have a close a look of your equivalent circuit of the transformer. All right, so this is the primary side, this is secondary side, and in between these two we don't have any electrical connection, so that we have shown it by giving a isolation between these two parts, all right, and this is what? This is magnetic coupling, where N1 and N2 are the number of turns of the primary and the secondary respectively. So we have some formula related to your equivalent circuit of the transformer, which is E1 equal to A times E2. What is A? A here is N1 by N2. Next, I naught is Im plus Iw. What is I naught? This current is I naught. I naught is equal to Iw plus Im. Next, E2 is what? V2 plus I2R2 plus JI2X2. V1 is E1 plus JI1X1 plus I1R1. I1 is equal to what? I2 by A plus I naught. So this is basically N1 I1. This is equal to N1 I naught plus N2 I2. N2 I2. So this is the primary MMF which is supplying the no load MMF plus load MMF. So if you ignore this no load wala part, so N1 I1 will become equal to N2 I2, which is primary MMF is equal to secondary MMF if you ignore this part. All right. So let me take this as dash. Let me take this as sorry, not dash. This is primary MMF equal to no load MMF plus secondary MMF. Now here N1 I1 dash is equal to N2 I2. So this can also be written as N1 I naught plus N1 I1 dash. So from here I1 will be equal to what? No load current plus I1 dash, the current which is a reflection of the load current. So if you see here the diagram, your I1 is equal to what? I naught plus I1 dash, and this I1 dash is what? Basically N2 I2 divided by N1. Let us move ahead. This is the phasor diagram. This is the phasor diagram of the transformer. So here I have taken the load to be a lagging type of load, where current I2, that is the load current, is lagging by an angle theta2 to the load voltage, which is V2. Now if you draw the phasor diagram, this part will be referred as no load power factor angle, which is phi naught, and here the angle between V1 and I1, where is V1? Yeah, V1 and I1. This is known as primary power factor. Primary power factor. So from here, your IW, which is this value, is equal to I naught cos phi naught. I naught cos phi naught. And what about Im? That is magnetizing current, or you can say I mu. This is also equal to I mu. This is I naught sin phi naught. And cos phi naught is what? No load power factor. Cos phi naught is no load power factor. All right. No load power factor. Similarly, cos phi 2 is what? Load power factor, and cos phi 1 is what? Source power factor. I hope these all points are clear to you. Guys, please do reply in the chat box whether this point all are clear to you or not. Please let me know. So moving ahead with the next part, that is the equivalent circuit referred to the means the secondary is referred to the primary. So here whatever component or the parameters that we have at the secondary side, we have referred that to the primary one. All right, we have referred to the primary side. So see here, what are the components that we can refer? So we have R2, JX2, here I2, sorry, V2, I2 and E2. So we have 1, 2, 3, 4, 5 components that we can refer to the primary side. So look at here. So your V2 dash means V2 is what? the load voltage when it is referred to the primary side. So dash will signify the reference of the parameter. So original voltage, which is V2 divided by N1 upon N2. Next, I2 dash, this is equal to N2 by N1 into I2. Next, E2 dash, original voltage, which is E2, N1 by N2. Next, R2, this is equal to, R2 dash is equal to R2 into your impedance are referred with respect to turns whole square. So it is referring to the primary side. So primary side has a turn N1 divided by secondary side has turn N2 whole square. Similarly, X2 dash is what? Actual value into N1 upon N2 whole square. And your Z2 dash, which is the series branch element of the secondary side. So Z2 dash is equal to what? R2 dash plus JX2 dash, which is basically this value. Done. So please try to remember all this formula, because this will going to help you solve the numerical type of question in the GATE exam. So moving ahead, the copper loss, losses in the transformer, the copper loss. So this losses is a variable loss where total copper loss is equal to what? Primary copper loss plus secondary copper loss. Means we have a winding now at the primary and the secondary. So that winding will have some resistance, and the current flowing in that winding, let us say I1. So I1 square into R1 plus I2 square into R2 will give you the total losses. Now once this parameter, means once the secondary is referred to the primary, or you can say that the primary when it is referred to the secondary, the total losses should not going to be changed. So here the total losses when it is referred on the either side will become PCU equal to I1 square into R01 and I2 square I2 square into R02 is the total copper loss. So where R01 implies that secondary is referred to the primary. So R1 plus secondary is referred, so N1 by N2 whole square. And similarly, your what is R02? So here 2 implies that your primary is referred to the secondary. So actual resistance of the secondary, that is R2 plus R1 N2 by N1 whole square. Now the copper loss at any load means what? Whatever data given in the question means, or you can say that whatever rating mentioned on the nameplate of the transformer will give you the full load power, or you can say that a full load value of the current, or which is also known as rated value of the current. So it is not always true that the transformer will operate at full load. Maybe it will operate at less than the rated value. So less than the rated value means, let us say I2 less than rated value means I2 rated. So here X is less than equal to 1. So this X signifies that the fraction of full load current. So basically that is the same value. So copper loss at X times of full load current, is equal to X square full load copper loss. Am I clear? So this formula is very, very important. Done? Now, here see the last point. Per unit resistance is equal to per unit full load copper loss. Means the per unit resistance of the transformer is also known as per unit full load copper loss. This is again very important point. Done. So let us move ahead with the next part, that is iron losses in the transformer. So iron losses, that the question that I have asked at the starting of this session, that what is iron loss and what losses are consisting in the iron loss. So iron losses are consist of hysteresis loss plus eddy current loss. So what is hysteresis loss? The losses which is occur due to reversal of the magnetic field, or you can say the due to reversal of the supply voltage or supply current. All right. So due to that reversal of the magnetic field, your losses will going to be happen in the transformer. So the hysteresis loss is equal to PH, which is equal to KHF B power X, that Bm is what? Maximum flux density, into V is the volume of the core, F is the supply frequency, and KH is the proportionality constant. Alright, and your Bm is what? The maximum flux density, which is proportional to supply voltage V divided by supply frequency. So this point is very important. If you not able to understand this point, my friend, you will going to face a lot of problem in the exam. So this point is very important, that the magnetic flux density is proportional to your supply voltage divided by frequency. Now here, based on the V by F ratio, the two cases will possible. Either the V by F ratio will going to be constant, or it will not going to be constant. So depending on that, the first case, when you take the constant over here, your your hysteresis loss will be proportional to F. All right, where V by F ratio is constant here. When you put V by F ratio constant, your hysteresis loss will be proportional to your frequency, and replacing this proportionality sign with the constant, PH will be equal to A into F, where F is the supply frequency. And if V by F ratio is not constant, then PH, which is proportional to V 1.6 F minus point power, means F to the power minus 0.6, or removing or replacing the proportionality sign, you will get A over here as a constant. Done. So in which this formula is very important. This formula is very important. Means most of the time, whenever you supposed to get the question from the losses in the transformer, then the cases that you will going to have is the first case. All right. So let us move ahead with the next loss, that is eddy current loss. So eddy current loss is given by KEF square Bm square into T square. So your again Bm is not proportional to V by F. Now depending on the ratio, you will going to have the two cases when V by F ratio is constant. If it is constant, your eddy current loss will be equal to will be proportional to F square, and replacing the proportionality sign, P will become B F square. All right. Now if V by F ratio is not constant, then P is proportional to V square, or P is equal to B V square. Am I clear? So let us move ahead with the next part, that is the other losses which are occurring in the transformer, that is stray load loss, dielectric loss. All right. Now remember one thing, that the rating of the transformer, which is given in kVA, because constant losses is proportional to the voltage and variable losses is proportional to the current. So total losses in the transformer is proportional to volt ampere. So the rating of the transformer depend upon the losses. Means the copper loss, which is a function of the current, and your constant loss, which is a function of the supply voltage. So multiplication of V into I will give you what? Will give you the rating of the transformer. Am I clear? So let us move ahead with the next slide, which is the test on the transformer. So we have two type of test, open circuit test and short circuit test. So these two tests on the transformer are helps to determine parameter of the equivalent circuit, voltage regulation and efficiency. All right. So in the open circuit test, what we are doing, we are finding, that is the objective, we are finding the parameter that is of the shunt branch, or you can say the no load branch, which is R0 and XM. In some book, we used to write R0 as RC or Rw. All are same. R0, Rc, Rw. And here Xm, in some book we used to write as X mu, that is the reactance. And the last objective is that to find out the constant losses in the transformer, that is core loss, constant loss or iron loss, all are same. Core loss, iron loss or constant loss, all are same. So here remember, this test must be conducted at rated flux condition, that is at rated voltage and rated frequency. So these tests are conducted at rated flux. So rated flux depend on the voltage and frequency. So if your voltage and frequency both are rated, then flux will going to be rated. So this test is performed on LV side while HV side is open circuited. So here we are supposed to find the or we are supposed to conduct this testing on the low voltage side, keeping HV side open. But one thing you should keep in mind is that even if we conduct the test on HV side by keeping LV open, the transformer loss means this loss, constant loss or a core loss, will going to be constant. Means if you conduct the test on LV side or HV side, other winding as a common as a open, the losses in the transformer, that is the core loss, will be equal. But due to some certain advantages, we are conducting this test on LV side. All right. So we require three types of meter. First one, watt meter, second voltmeter and ammeter. So watt meter will give you the core loss, which is Pi. Voltmeter will give you the rating, will give you the voltage reading over here. So here VOC is what, basically this is V1, or you can say this is V1 rated. And this ammeter reading, so your ammeter here will give you the current I0. And we are supposed to find the iron loss, this R0 value and this Xm value. So see how we will going to find. From the this iron losses, first one, from the iron losses, can I say your Pi is equal to, see here, your Pi is equal to this voltage directly appearing across this branch, across R0. So can I say Pi iron losses, which is the active power, you can say, means whatever losses occurring in the machine or in the device is basically a form of the or you can say the part of the real power. So Pi, which is real power, is equal to V1 square whole divided by R0. So from here R0 is equal to V1 square by Pi. So we have got the two values, means the objective that we are supposed to be perform, that we have got. The first part is from the watt meter, and the second part we can calculate from here. So R0 we have calculated. Now next thing, we are left with the Xm. So how we will going to find the Xm? See, Z open circuit is what? Magnitude of V1 and magnitude of I0, or you can say V1 by I0 whole magnitude. So when you divide these two, you will get the magnitude of ZOC, means the equivalent impedance from here. Equivalent impedance from here. Is it clear or not? Is it clear or not? Or else we can do one more thing. See, we have got the R0 value here. So can we get our I1 value? Can we get I1 value? Yes. we can get the I1 value here. So, or you can say IW. So, your IW is what? See, second, PI that we know, this is equal to V1 into IW, isn't it? These two are equal. These two are equal. So, from here, IW is what? IW is equal to PI divided by V1. So, we have obtained IW. So, from here, I can say that I naught, which is root over IW square plus IW plus IM square. So, from here I can get IM as root over I naught square minus IW square. So, I have got the IM value. So, from this IM, I can calculate this XM. How? This XM is equal to magnitude of V1 whole divided by IM. So, these are the steps in which you will going to find the parameters. Alright, so let us move ahead with the next part, that is the separation of the losses. So, what do you mean by separation of the losses? Since the constant loss are consisting of two parts, hysteresis and the eddy current loss. So, with this test, we cannot find the individual losses. Means, suppose your iron losses come out to be 100 watt, then what part of 100? Will be your hysteresis loss, and what part of your 100 will be your will be the eddy current loss. So, that we are not able to directly find out from this test. So, for that we need to use the certain technique in which we will going to separate out these losses. How? Here conduct test on V by F equal to constant. So, if V by F equal to constant, this implies Bm is equal to constant, isn't it? So, your iron loss, which is hysteresis loss plus eddy current loss, will be equal to what? AF plus BF square. So, taking out F common, from here you will get Pi by F is equal to A plus BF. So, this is what? This A plus B times F, this is equal to your straight line equation. Okay. So, this is Y, this is C, and this B is what? Slope, which is M, and X is what? Frequency. So, see, if I plot the curve of the straight line, can I say the P by F is equal to what? A plus BF. See here, A plus B times F. So, this is Pi by F axis and this is F axis. So, the curve will be like this. Okay, just a second. I hope this is visible to you. Okay, all right. So, this part, the intercept at y-axis will give you the A value. Means the distance from origin to this point is what? Basically A value, isn't it? Or let me write here. Just a second. Let us take this as origin. This is what to take here? X. All right. So, this distance Just a second. This distance is A. All right. And the slope which is theta, or the slope which is m, which is equal to tan theta, is what? Is equal to B. Is equal to B. So once you're going to plot the curve, once you going to find the pi for different values of the frequency and plot them here in the graph, you will going to get the intercept as well as this slope. So from here I can directly write that your AD current, the hysteresis loss is equal to AF. So for any frequency, I can find the hysteresis loss, since A that we have obtained from the graph, and AD current loss, which is equal to B F square. So for any frequency, I can find the AD current loss as well. So with this steps, you can separate out your total losses, which is Pi, in terms of PH and PE by using this formula. So let us move ahead with the short circuit test. So the main objective is to find the total resistance and reactance of the transformer when referred to the winding in which the measuring instrument are placed to conduct this test. And the next objective is to find out the variable losses in the transformer, that is the copper loss. Now remember, this test should be conducted at rated current condition. So this is very important. Rated current means this test should be conducted at rated current so that we can find the rated copper loss. All right, so that we can find the rated copper loss. But it is not always true that we have to perform this test at rated current. It is not always true. It is recommended that we should run this test at rated voltage, but sometimes it depend upon the manufacturers, or depend upon the person, that this test he or she may conduct at less than the rated current. All right. Now this test is conducted at HV side, while LV side is short circuit with a thick conductor. So here the measuring instrument should be connected at the HV side. All right, and the LV side should be short circuited, and the losses occurring here will be referred as the copper loss. Now we can do the reverse of it, means we can connect the instrument, or you can say that a meter at the low voltage side as well, by keeping the high voltage side short circuiting. Then in that case, whatever losses that you are getting, that is the copper loss, is same as that of the high voltage side losses. Am I clear? So this test can be conducted on both sides, but my dear friend, due to certain advantage, this test is conducted on HV side. Am I clear? So let us move ahead. This is the equivalent circuit where VSC, this is the supply voltage when it is referred to the secondary side. All right, this is supply voltage when it is referred to the secondary side. And this R equivalent is what? This is, let us say this is R02 and this is JX02. So what is R02? R02 is, let me write here, R1 N2 by N1 whole square plus R2. So here I have referred, or you can say that my HV that I have taken on the secondary side, and my LV which I have taken on the primary side. So I have referred the LV side to the secondary side. All right. Now see here, this JX2, this is equal to, let me write here, this is equal to X1 N1 by N2 whole square plus X2. Let us take the current here is I2, where I2 is X times of I2 rated, and here the load is एक second. Okay, so here V2 dash is 0 volt. Here V2 dash is 0 volt. Let me write here. Okay, not V2 dash, this is V2. This is V2. Just a second. Here V2 is equal to 0 volt. Now look at here. We have a 3 meters, all right. So the wattmeter will read you the will give you the copper loss, which is PSC. Voltmeter reading will give you VSC, which is much less than the rated voltage. Which is much less than the rated voltage. You can say that this VSC is nearly equal to the 5 to 8% of the rated voltage. Now emitter reading is IISc, that is the rated current, or you can say the short circuit current. All right. So please remember that the rated voltage does not implies that the current will be rated. The current rated means the current value, whether the current will going to be rated or not, will depend on the load that you are connecting. If your load is rated, then the current will be rated. If the load is not rated, then your current will not going to be rated. Am I clear? So the voltage, the rated voltage does not implies that your current will going to be rated. Am I clear? So let us move ahead. How we will going to find the this element R equivalent and X equivalent, which is R02 and X02. So how we will going to find? See, this is the losses which is occurring in the transformer. So can I say PSC, this is equal to short circuit current square into R02. So from here I can say R02 is equal to PSC divided by ISC square. So we have all the values PSC and ISC. So from here I can get the R02. Second, ZSC, which is what? Magnitude of supply voltage, which is VSC divided by current. So from here you will get the ZSC. And the third step is that we have got PSC, we have got R02. Next we are left with X02. So how to find X02? Your ZSC, which is equal to root over R02 square plus X02 square. So from here I can say that X02 is equal to root over ZSC square minus R02 square. Done? Where R equivalent, X equivalent and Z equivalent are the referred parameters to the high voltage side. And the next important point is power factor on short circuit is cos phi SC, which is R equivalent by Z equivalent. And comparing this with the with our circuit, your R equivalent is what? R02 divided by Z equivalent is what? ZSC. Done? Am I clear? Any doubt in this? Guys, please replies and please share the session link with your friends so that they can join as fast as possible. Okay. So let us move ahead with the efficiency formula. Efficiency in the transformer is what? Basically output power by input power. So what is input power? Input power is output power plus losses. So we have a general formula of the efficiency. Now note point, efficiency at any fraction of full load current. Any fraction means X of full load current will give you efficiency at X times of full load is equal to X kVA, means the rating given on the question or the rating given on the transformer is the kVA full load into cos phi upon X times of kVA into full load into cos phi plus iron loss plus x square times of PCUFL, where Pi is core loss, iron loss or constant loss, and PCUFL is what? Full load copper loss, means this part. This part. Done. Now see here, efficiency at full load. This is very important point. Efficiency at full load means x value is what? X value is 1. We have written here na, I2 is what? X times of I2 rated. If I2 is full load, this means that I2 is what? I2 rated then. So this value is equal to x times of I2 rated. So from here, x value will become 1. Am I clear? So your when x is 1, so replace x equal to 1 in this formula, you will get the efficiency at full load condition. Efficiency at full load condition, which is this value. So this formula is very important. Let me inbox this. Okay. Next is condition for the maximum efficiency. Now my dear friends, this topic is very, very important considering to the GATE exam question. What is condition for the maximum losses? The condition is that whenever copper loss will become equal to iron loss, or let me write here, is will become equal to iron loss, then your maximum efficiency will going to be occur. Please do not say that your iron loss will equal to copper loss. No. Here copper loss has to be made equal to the iron loss because iron loss is a constant loss. Guys, please hit the like button so that I can know that how many students are live here. Please hit the like button and please share the session link with your friend. All right, so come back here. Your copper loss is what? At any load, this copper loss is equal to x square times of PCUFL, which is equal to iron loss, which is Pi. So from here, x will be equal to what? Root over Pi upon PCUFL. So whenever x value will be this, your machine will, your transformer will going to give the maximum efficiency. Done. Now, what is the value of the maximum efficiency? What is the kVA value at the maximum efficiency? See here, kVA is load. kVA load for the maximum efficiency will be S eta max equal to S of the transformer into Pi upon PCUFL. Means if the rating given in the question is 100 kVA, let us say, and your X value is 0.8, then the load that you are supposed to connect across the transformer will be S eta max 0.8 times of 100. So this will give you 80 kVA. So if you connect the 80 kVA load across the transformer, then you will going to have the maximum efficiency. So let us move ahead. Voltage regulation, again one of the very important topic. What is voltage regulation? Means how effectively we can regulate the voltage is known as voltage regulation. Now in our machine, you can say, in the transformer, you can say this voltage regulation has to be minimum as much as possible. All right, so let me give you one analogy to you. Suppose I am giving you 100 rupees of note and I am saying that please give this 100 rupee note to the other person. So definitely you are supposed to give that 100 rupee note to the other person. Other person means the whole amount you are supposed to give to that particular portion, to the particular person. Now let us assume that some part of money, means out of 100, let us say some 5 rupees that you have lost in between the journey. So that 5 rupees is what? You are supposed to give the 100 rupees, but you are giving that person 95 rupees. So that 5 rupees is what? Is basically a part of your money which you have lost. Okay, which you have lost. So that 5 volt, or sorry, not a 5 volt, that 5 rupees is basically what? The drop across the series branch, or you can say the drop in the transformer. Alright, so whatever money I am giving, that money you are supposed to give to the other person. So in the same way, whatever voltage you are generating, let us say E2, that voltage you are supposed to give to the load, but that is not possible. We are getting V2 which is less than E2 because of this resistance R02 X02. So this is called secondary side impedance, and this will give you the voltage drop. Let us take here the current is I2. Current here is I2. I2 is what? X times of I2 rated. Now see the formula here, the voltage regulation, the general formula, which is no load voltage minus load voltage divided by no load voltage. Now what is no load voltage? When the load is not connected, the current value will be 0. So can I say V2 under no load will be equal to E2, because no drop will going to be occur here. So this formula can be written as E2 minus load voltage, which is V2 divided by E2. So this is known as per unit voltage drop. Now look at here, the voltage regulation is having the formula I2 R02, just a second, I2 R02 cos phi plus I2 X02 sin phi whole divided by E2, whole divided by E2. Now what is I2? I2 is X times of I2 rated. So replace this I2 with X times of I2 rated. Here you will get X times of I2 rated R02 whole divided by E2 cos phi plus I2 rated X02 whole divided by E2 into sin phi. Now E2 divided by I2 rated is what? Z2 base. E2 divided by I2 rated is what? Z2 base. So Z2 base will here R02 divided by Z2 base is what? Basically R per unit. So here R02 divided by Z2 base into cos phi plus X02 upon Z2 base into sin phi. R02 by Z2 base is what? R per unit, and X02 by Z2 base is what? X per unit. So the all formula that I have derived here are same. Alright. So this formula will give you the per unit values, and when you are going to multiply it with 100%, you will get the percentage voltage regulation. So this is the per unit voltage regulation, but if you want to convert into 100%, or you can say the percent, just multiply with 100, you will get the percentage voltage regulation. So this formula is very important. This formula and this formula. This is in per unit. This is in per unit. Am I clear? And where X is less than equal to 1. For the full load, means they will specify in the question whether the voltage regulation that we need to find is on the full load or at the half load or at any particular load. So for that you have to put those value or that value in the voltage regulation. Done? Where phi is what? This is the power factor angle between V2 and I2, or you can say that Gopal Gupta, yes, all clear. So here phi is what? Power factor angle, or you can say that the load power factor. So let us move ahead with the next part. Okay, one more thing, the important point. Whatever formula that I have written here, I have considered that the load is a lagging type of load. But what if the load is leading? So for that reason, you have to replace phi with negative sign. If the load is lagging, then power factor cos phi or the power factor angle will be positive. If the load is leading, that is RC type of load, then the power factor angle you have to be take as negative. So for the negative power factor angle, replace phi with minus phi. So you will going to get your formula. All right. So let us move ahead. Condition for the maximum voltage regulation means at what condition the voltage regulation will going to be maximum, and this is not at all desirable, because if the voltage regulation is maximum, the drop across the series branch will be maximum. So what is the condition? Condition is that the power factor phi, that is the load power factor, is equal to the internal impedance angle of the transformer. So what is internal impedance angle? This is theta. So R02 and this is X02 and the hypotenuse is Z02. I hope this is clear to you. Now this is the condition. But what is the value of voltage regulation? This is equal to X times of Z02 in terms of per unit. Very important formula. One is this and other one is this. Done. Next is condition for zero voltage regulation, which is most desirable in any machine or in any device. So condition for zero voltage regulation means what? There is no voltage drop in the device. So this means that this can only occur when power factor angle plus internal impedance angle sum up to the 90 degree. Sum up to the 90 degree. Very important. All right, where phi is equal to, or you can say your phi is equal to 90, or let me write here, cos phi is equal to X02 divided by Z02. Please do not say that, sir, in the power factor we will be having resistance at the numerator, na. But my dear friend, here phi is what? 90 minus theta. So because of that, the reactance will come, and in the denominator impedance will come. So these two conditions are very important. Please try to keep these two formula in your mind. All right. So this is the power factor or voltage regulation versus power factor curve. It is like ideal case. Yes, it is like your ideal case, you can say. So here this is the curve between the voltage regulation versus power factor curve. So here I have shown three curves depending on the load. If the load is means the X value is 0.6, your curve will be the black one, which is somewhat lower. If you increase the load to 0.8, the middle curve will give you the the voltage regulation versus power factor curve, and the last one when the load factor, the load fraction is 1, means the machine is running at full load condition or at rated value, then the voltage regulation will be this one. All right. So from here I can say that if you increase the load, your voltage regulation will going to be increased, and that is for sure. It has to be happen. Why? Because your voltage regulation depend upon the current, isn't it? If the current is increasing, this means that the load is increasing, and if the load is increasing, the voltage regulation will going to be increased. Am I clear? Any doubt in this? So see, let me take this black wala curve, na. Now see here, this is the maximum value of the voltage regulation. So this is VR maximum here, and this is occurring here. This is the power factor angle axis, and this is the voltage regulation axis. So here voltage regulation is maximum, and this is occurring at this particular load. So here your phi is equal to theta, or you can say your power factor cos phi, this is equal to R02 divided by Z02. Yani cos phi equal to cos theta, so and cos theta is R02 by Z02. Alright, so this part from here, from origin to the right hand side is considered as a lagging power factor. This is a lagging power factor, and left hand side is referred as a leading power factor. So your maximum voltage regulation is occurring at the lagging power factor. Am I clear? Now see this point. Here voltage regulation is what? 0. So at what power factor it is occurring? This is occurring for cos phi equal to X02 divided by Z02. Please do not get confused with the formula. At 0 voltage regulation, in the numerator X02 will come, and for the maximum voltage regulation in cos phi R02 will come. Alright, so I can conclude that maximum voltage just a second. So maximum voltage regulation occurs at lagging power factor. Here zero voltage regulation occurs at leading power factor. At leading power factor. I hope this point is clear to you. So let us move ahead with the next part, that is auto transformer. Alright, let us come to the auto transformer. So what do you mean by auto transformer? Whenever the power is transferring through the inductance or you can say through the induction as well as through the conduction, means we can directly transferring the power, and also we are transferring the power through the magnetic domain. So those two power transfer is known as auto transfer, or in the other way you can say that when the power is transferred through the current, and also when the power is transferred through the magnetic domain, then those two power referred as the auto transformer power, you can say. So here this is HV side of the transformer, and this is the LV side of the transformer, where AB's part, A and B part is known as series winding, BC part is known as common winding, NH is what? Number of turns of the winding AC, means this total turns is known as is having NH value, and similarly NL is what? Number of turns in the winding BC, means this turns is having NL value. All right. Now from the high voltage side, the current which is coming is IH. Please do not say that this IH is having the higher value of the current, whereas IL is having the low value of current. It is not that. I implies that the current coming from the HV side, and L implies that the current going into the low voltage side. Am I clear? Now what is auto transformation ratio? A auto, which is A not auto. A auto is what? A suffix A, which is equal to high voltage divided by low voltage, which is equal to NH upon NL, which is equal to 1 upon K. What is K? K is the transformation ratio, which we oftenly use in the two winding transformer. So let us move ahead. That is the KVA rating of the transformer. So KVA rating of the transformer is having the formula equal to A auto upon A auto minus 1 into kVA of 2 winding. So we can also write this as 1 upon, means divide A auto, you will write, you will give, you will get 1 upon 1 minus 1 by auto, and 1 by auto is what? K, into kVA of 2 winding. This formula you have seen in most of the book. All right. So let us move ahead with the next part. That is the total power which can be transferred. That is the kVA power from the auto transformer which we can transfer, is that VHIH is equal to VLIL. So the primary kVA supplied is equal to the secondary kVA. So VHIH is equal to VLIL. So from here it is clear that if VH is greater than, since VH is greater than VL, this implies IH is less than IL, right? So the thing that I was saying at that time is IH does not says that the current value is higher here. All right. So from here we can conclude the result. So the part of VHIH and VLIL is what? Inductive transfer, which is VLIL minus IH, and the part of conduction transfer is VL into IH. Try to remember this formula. Now inductive transfer divided by total transfer is what? 1 minus 1 upon A, or you can say 1 minus K, and conducting or the conduction transformer is what? This is equal to K. As simple as that. Remember, the auto transformer has higher efficiency, lower per unit impedance and lower voltage regulation as compared to the two winding transformer. This is very important considering to the your Viva or the interview. All right. So this point is very important. Chandrasekhar. Okay, so let us come to the 3 winding transformer. Please do not consider this as a 3-phase transformer. This is the 3 winding transformer. So what do you mean by 3 winding transformer? Let me add a page here. So 3 winding transformer means if you have a transformer core like this, where this is the primary side, so at the primary we have a voltage applying as a V1 and current here I1 and number of turns here as N1. Then we have a two extra winding in the same core, which is having a voltage, let us say here, okay, let me draw one more. Here we have a voltage V2, current here I2 and number of turns here N2. Let us say here we have a voltage V3, current here I3 and number of turns here as N3. So in the same core we have 3 windings, 1, 2 and 3. So this is known as 3 winding transformer. If you connect one more winding over here in the same core, then it will become 4 winding transformer and so on and so forth. So the voltage per turn V1 by N1, V2 by N2, V3 by N3 all are equal. MMF balancing equation, N1 I1 means the MMF supplying from the primary side, or you can say that the MMF supplying from the primary side is equal to the secondary MMF plus the tertiary MMF. So here I have neglecting the magnetizing current, means the IM or you can say that neglecting the no load current. So you will get N1 I1 equal to N2 I2 plus N3 I3. So from here N1 will be equal to N2 by N1 into I2 plus N3 by N1 into I3. Thus we are having the same formula. Just divide the right hand side with N1. All right. And the kVA balance equation is the primary side volt ampere is equal to the sum of the secondary and the tertiary VA rating. All right. So let us move ahead with the next part, that is the parallel operation of transformer. So here I have taken a general case where I have taken the two transformer in which the secondaries of the each transformer are connected in the parallel. So the parallel operation transformer means what? All the transformer are connected in the parallel, means the primary of the transformer of all transformer are connected in parallel and the secondary of all transformer are connected in the parallel. So we have the general circuit diagram like this. Now the main idea here is that we need to transfer, means here the transformer has to supply the power or kVA to the load. So we have a load over here. Let us say the load impedance is ZL, voltage at the load is VL and current at the load is IL. Let us take this as transformer 1. Just a second. Let us take this as transformer A and this as transformer B. Transformer B. Then what amount of power is supplied to the load by the transformer A, that we need to find, and what amount of power that is supplied by the transformer B to the load. So for such type of parallel operation, we should first know what is load value. What is the load value that we are supposed to operate? So your load value should be given to you or should be known by you. So let us take the SL as magnitude of SL at an angle SL. Okay. So I have written the complex value of the load in terms of polar. Now here SA, the complex power supplied by the transformer A is equal to SL into ZB upon ZA plus ZB conjugate, and similarly SB will be equal to SL ZA upon ZA plus ZB conjugate. All right. Now one important thing you should keep in mind, that for lagging load, angle SL is greater than 0. Means we have to take this angle positive for the lagging load, and for leading load this angle SL will become negative. This angle will become negative. Am I clear? Any doubt in this? And what is ZA, ZB? This is the impedance of transformer A. So let me write here. ZA is RA plus JXA and ZB is what? Impedance of the transformer B. That is the secondary impedance. My dear friend, the secondary impedance. RB plus JXB. So substitute all this value, you will come to know that what part of the load has been supplying by the transformer A and in the same way transformer B. So with this we have completed the all formulas related to the transformer. Now let us come to the induction machine. Now this is again, this chapter consists of belongs to the two stream, that is EE and IN. So in which this is the weightage and the important topics is that I have written over here. So you can pause and you can read the important topic. All right. So let us move ahead. We have a general term related, the general concept related to the three-phase induction machine, that is production of the rotating magnetic field. So whenever you have a three-phase balancing current and the balancing load, then the three-phase flux will going to be generated, and due to that three-phase flux which is rotating or revolving inside the stator core at a synchronous speed will give you the power transferring from the stator to the rotor side. Anyway, you can stop the video and have a look of this part. So moving ahead, the resultant MMF is what? Fr, which is equal to 1.5 times of Fm cos omega t minus theta, where Fr is the resultant MMF and Fm is what? Maximum MMF. Now, synchronous speed and slip. Synchronous speed Ns is equal to what? 120 F by capital P. So F is supply frequency and P is number of poles. Guys, please like the session, and I am seeing very less number of students over here. Please share the session link with a friend, guys. Please do it once. Please share the session as much as possible. Okay, so as soon as I said, I am seeing that one like has increased. Okay. So please be interactive in my session, student. Definitely I will going to give you my 100%, so that you will have to give not a lot amount of effort to understand the thing, but for that you have to be present here for all the session. All right, for during the entire session you have to be present here. Otherwise if you lose some part, then definitely the thing will not going to come to your head. All right, so let us come to the part where we are supposed to find the slip value. What is slip? Slip is synchronous speed minus rotor speed, means at what speed the rotor is rotating, divided by Ns. All right, so Ns is synchronous speed in RPM, Nr is rotor speed in RPM, this Nr. Okay, now some important point. Speed of stator field with respect to stator. So stator field rotate at a synchronous speed and the stator is stationary in the induction machine. So this is 0. So this will give you Ns value. Speed of the rotor field. So rotor field is also rotating at with a synchronous speed Ns, and the stator is stationary. So this will give you Ns. Speed of rotor with respect to stator. Rotor means Nr. Stator speed is 0. So this will give you Nr. Speed of stator field with respect to rotor means stator field speed is Ns. Rotor speed is Nr. So this value is Sns. From here, Ns minus Nr is Sns. Speed of rotor field with respect to rotor, Ns minus Nr, again this value is Sns. Now one important thing is that from the fourth and fifth point, that both speeds are same. This means that the relative speed between the rotor field and stator field is 0. And this is the one of the criteria for the proper production of the torque. Now rotor speed Nr is equal to synchronous speed times 1 minus S. Very important formula. Ns, just a second. Ns 1 minus S. And the last is the rotor of the induction motor never runs at synchronous speed because your Nr is always less than Ns. Otherwise, EMF will be 0. So whenever your EMF at the rotor side becomes 0, then your induction machine will try to stop itself. So let us move ahead. This is the equivalent circuit of the three-phase induction motor, which is same as that of the equivalent circuit of the transformer. This is the stator side and this is the rotor side. In the transformer, this is known as the primary side of the transformer and this is referred to the secondary side of the transformer. So since the working of the transformer and the induction machine both are nearly equal, so we can represent the equivalent circuit of the induction machine in terms of the transformer. All right. So this is the equivalent circuit referred to the stator, means here rotor has been referred to the stator side. So the parameters that we have referred is R2 dash 1 by S minus 1, this is 1 by dash minus 1, and this is X2 dash, this is I2 dash, and this is E2 dash. Alright, so this dash implies that the referral of the parameters to the other side. So let us move ahead. The power flow in the induction motor. Power flow in the induction motor. So this is the induction machine, which is a typical circuit, you can say that. Typical circuit, not a circuit, the typical induction motor that you have seen at your home itself. This is the squirrel cage type of induction motor, which is known as a low power induction motor, which you oftenly see to pump the water. Okay. So the first part is the stator, and this is your rotor, where with the shaft you will going to connect the load. So at the stator you will supply, you will give the power input. So at the stator, whatever input you are giving is known as power input, or you can say the supply input or stator input. So this is the active power to the stator, which is PSI. Let us say PSI. This is also equal to P input. Now after that, the power will move ahead and it will come across the stator copper loss and stator iron loss. Since the stator are made up of iron, so the iron loss will going to be occur, and at the stator we have a winding. So due to that we will going to have one another losses, which is known as stator copper loss. Now after deducting these two values with stator input, the power will go to the rotor side. Means this rotor is basically inside of this stator, but to have a clear idea, I have taken out the stator part, or bring out the stator part to here, so that we can visualize the thing in very simple manner. Now the power which will move ahead here after reducing this value is known as active power supplied to the rotor. So this is rotor input, which is also known as stator output. Now here, if this is stator, suppose this is your stator and this is your rotor, and the rotor is rotating. So to the movement, or you can say that to such that your rotor will rotate freely without any friction, there has to be some air gap. So due to that air gap, this rotor input, the stator output, is also known as air gap power, or in some case we can write it as PG. So this all notation are will imply the same thing, which is the rotor input. Now after that, the rotor will have a winding and a core. So once you will deduct the rotor copper loss with the iron loss, you will going to get the gross mechanical developed power. So this is what gross mechanical power or gross mechanical developed power, which is referred as PGMD. This you have seen or not? You have seen or not? Now after that PGMD, your shaft is connecting, na? So this shaft will going to have one more losses, which is friction and windage. See here, friction and windage. So after deducting these losses, friction and windage, with the gross mechanical developed power, you will going to get the shaft power, which is PSH, output power, which is P out, or this is also known as net power. So this is the power flow in the induction machine, which I have shown here as well. Alright, so let me write all the formulas here. Electrical power, here I have shown the diagram for the induction motor, because in the syllabus we are having the induction motor. So for the induction motor, the power input will be electrical and the output will be your mechanical. So the input electrical power will be what? √3 times of line voltage, which is VT, into line current IL cos theta. Stator copper loss, let us say PSCU, stator core loss, and after that you will going to get the air gap power or rotor input power. So this rotor input power is what? PG. This is equal to PSI minus, let us say this total losses as PSL minus PSL. So this is known as air gap power or rotor input power. So this rotor input power, when you going to subtract with the rotor copper loss, which is PCU. PCU implies the rotor copper loss itself. You need not have to write R in the subscript. PCU implies that this is copper loss. With the stator copper loss, we need to write S, but with the rotor, we need not have to write. So after deducting the rotor copper loss, you will going to get the gross mechanical developed power, which is PGMD. This is equal to rotor input power, which is this power, PRI minus PCU. Now when you subtract with friction and windage loss, this PGMD, here you will get PGMD minus friction and windage loss, you will get P out, P naught, which is P shaft, which is P net. Okay, P net, ignore this one. So this is the gross, this is the actual power that you are getting at the shaft, or you can say at the mechanical shaft. Next, rotor equivalent circuit. So this is the rotor equivalent circuit of the induction motor, where this is the induced EMF at the rotor, current flowing at the rotor side or current flowing through the winding of the rotor, which is I2. This is the leakage reactance of the rotor, and this is the equivalent resistance of the rotor, which is R2 by S. Now the per phase current at any slip means S, I2, the magnitude will be equal to E2 divided by, I am writing the magnitude here, which is equal to E2 divided, I2 will be equal to E2 divided by root over R2 by S whole square plus X2. This is X2. This is X2. Next, cos theta 2, that is the power factor. What is power factor here? Resistance, which is R2 by S whole divided by root over R2 by S whole square plus X2 square. Next, per phase power input to the rotor means the power here which is entering at the rotor, which is PRI, PG, stator output or air gap power, all are same. PG, in some book the air gap power is used to write PG, will used to denote with PG or PAG, both are same here. So the per phase rotor input PG will be equal to what? See, 3 into magnitude of I2 square into R2 by S. This is the real power, na? So the real power are given by the resistance. This X2 will give you the reactive power. So this is the rotor input, or else this can also be written as three into, this is the per phase equivalent circuit. My dear friend, this is the per phase equivalent circuit, and to convert or to find the total power, which is a three phase power, we need to multiply with 3. This I2 square into R2 by S is what? Per phase. When you multiply it with 3, you will going to get the 3 phase power. So 3 times of, this is I2 na, so take the magnitude from here, you will get E2 square whole divided by R2 by S whole square plus X2 square into R2 by S. Done? Clear, my dear friend? Now PG or PAG or PSO or PRI all are same and is the power transfer from the stator to the rotor that we have seen. All right. Try to remember this all formula. This all formula is very important. Now the rotor ohmic loss, which is the copper loss, this is equal to 3 times of I2 square into R2. Please do not write R2 by S. Do not write R2 by S because the resistance of the copper is what? R2. The resistance of the copper, just a second. The resistance of the copper is what? R2. But R2 by S is what? This is the equivalent resistance for air gap power. Which is this value, all right. So to get the copper loss will be given by the resistance. So your copper loss due to of the rotor will be equal to 3 times of I2 square into R2. Now next is internal mechanical developed power, which is PGMD. So this is equal to rotor input minus rotor copper loss, which is PCU. Okay. Now how to get the copper loss from here? Copper loss, not a copper loss, rotor input. Rotor input we can get by using this formula. All right. So let us move ahead with the next term, that is internal or gross torque developed per phase. So T equal to internal mechanical power developed in the rotor. Okay. So let me rub this part. Because the torque cannot be a per phase. This is the mechanical parameter. The torque is what? Mechanical parameter. And the voltage and current are the electrical parameter. So the electrical parameter can be referred in terms of the per phase, but the mechanical parameter cannot be referred in the per phase. So my dear friend, the internal or gross torque that we need to find, which is equal to internal mechanical power developed in the rotor divided by rotor speed. So this is equal to what? PGMD divided by omega R. So this can also be written as PRI divided by omega S. These two values are same. PGMD by omega R, PRI by omega. Try to remember in the denominator part, means with respect to power, omega R will come or omega S will come. This totally be a point of confusion. So please try to be specific with the formula. So with PGMD, omega R will come, and with PRI, omega S will come. Am I clear? Done. So let us move ahead. The output power P naught, which is shaft power, is equal to what? PGMD minus friction plus windage loss. Done. So output or shaft power, this is equal to what? P shaft divided by omega R. Next, air gap power. So air gap power is what? We can write air gap power as which is a rotor input power, or you can say that air gap power we can find directly by using the stator input minus stator copper loss minus stator core loss. My dear friend, I have one question for you. Why we have not considered the core loss for the rotor part? Why we have not considered the rotor the rotor core loss in the rotor? Why we have ignored the rotor core loss? Please write in the comment box. So efficiency of the three-phase induction motor, which is equal to, efficiency is equal to output power divided by input power into 100%. So output of the induction motor is what? Shaft power, isn't it? PSH, which is this value, and divided by input. Input is what? Output plus losses, na? So output is PSH and losses is what? Fixed losses and the stator rotor ohmic losses, which is known as copper loss. Copper losses. So here losses is PF plus P naught H into 100%. All right. So this is the Thevenin equivalent circuit. Now we are going to enter into the important formulas where we are converting. Just a second. Where we are converting the equivalent. कहाँ गया? Yeah, the equivalent circuit, which is when it is referred to the stator side, into the Thevenin equivalent, otherwise such that we can derive some formula, or we can have some formula. All right. So here, once you referred the rotor to the stator, we will going to have the formula like this. See, here you have referred the rotor to the stator, and this part is the this part is the stator. This part is the stator. So considering this as a load, from here we will going to find the Thevenin equivalent parameter. See, this is the Thevenin equivalent parameter. So here I have taken this as node A and here node B, and we are finding the Thevenin equivalent, which is equal to VTH. This is ZTH, and the current is I2 dash, which is equal to I1 dash, and this is the rotor parameter, which is R2 dash by S and X2 dash. So see how we will going to find. Your VTH is equal to V1 supply voltage JXM upon JXM plus JX1 plus R1. So this is equal to V1 JXM upon R1 plus J capital X1. So what is capital X1? Capital X1 is XM plus small x1. Now this VTH is equal to, see here, this VTH is equal to, nearly equal to V1 times of XM, or let me write here, V1 times of XM by X1. Here X1 is much greater than R1. So when you ignore this R1, this JJ will going to be cancelled out. So XM by X1 you will get. Now ZTH, how we are going to calculate ZTH? ZTH is what? The parallel combination of these two plus sum of this. And one more thing, for the analysis, we have ignored this part. For the analysis, we have ignored this part. Okay. So by ignoring that, let me write here. Just a second. Ignore RSC for the analysis. All right. So whatever formula that we are writing here, we are writing by ignoring this RC. Okay. Now ZTH will become equal to JXM in parallel with, means this part JXM, when you short this one, just you are finding, means you are using the basics of your transformer, of your network now. So this JXM, when you short this voltage terminal, R1 plus JXM will come in parallel with the JXM. So from here, JXM will be, ZTH will be equal to JXM parallel with R1 plus JX1. So this is R1 and this is J small x1. Okay. This is J small x2 dash. Just a second. Okay. So let us find here. This will be Jxm into R1 plus Jx1 whole divided by Jxm plus Jx1 plus R1. So this is equal to, just a second, this is equal to Jxm R1 plus Jx1 whole divided by Jx1. Again, I have clubbed this xm, capital Xm and small x1 with capital X1 and ignoring the same R1. So you will get in the denominator you will get Jx1. So this is equal to, this is nearly equal to R1 Xm by capital X1 plus Jx1 Xm by capital X1. Okay. Where X1 is Xm plus small x1 and x1 is much greater than small r. So considering all this, considering these 2 points, you will going to get this result. All right. So here, from here, RTH value will be what? This is R1 Xm by X1 and XTH will be what? Small x1 Xm by X1. Try to remember this formula. This formula is very important. All right. So this part is RTH and this part is XTH. Now electromagnetic torque, it is denoted as TE or simply T, or in some book we used to write it as TEM. Now this is equal to the rotor input, this is equal to gross mechanical developed power divided by omega r. So this is equal to PGMD divided by omega r, or this can also be written as PRI divided by omega s. So due to, since we know that this T is what? This T is a mechanical quantity. So here the power that we need to consider is 3-phase power. So 3 by omega s into magnitude of I2 square into R2 dash by s. So dash implies that we are writing the formulas when the rotor is referred to the stator side. So this is equal to 3 by omega s into, just a second, VTH whole square whole divided, means in this formula we are finding the parameters, that is electromagnetic torque. Am I clear? So VTH whole divided by RTH plus R2 dash by S whole square plus XTH plus X2 dash whole square into R2 dash by S. Now TEST means the electromagnetic torque at starting, or it usually referred as TST. So at starting the slip value will be 1. Why, sir? Because at the starting the rotor speed will be 0. So slip will be 1, as ns minus nr upon ns will be 1 due to nr equal to 0. So at starting, let me write here. So let me write the formula here. So TEST or TST, this is equal to, uh, just replace this S with 1. You will get starting torque 3 by omega S into VTH whole square whole divided by RTH plus R2 dash plus XTH plus RX2 dash, just a second, X2 dash whole square into R2 dash. So starting means at starting NR equal to 0, and this implies slip will be equal to 1. Always at starting your slip will be equal to 1. So let us move ahead. Maximum means this is the slip corresponding to maximum torque. All right. So this is equal to R2 dash, R2 dash whole divided by RTH square plus XTH plus X2 dash whole square root over. This is the exact expression for the slip corresponding to maximum torque. And what is the value of the maximum torque? This is equal to 3 by omega S into VTH square upon, see here, we have a formula na, RTH plus R2 dash divided by SMT. So replace S with SMT, you will get maximum developed torque. So whole square plus XTH plus X2 dash whole square into R2 dash upon SMT. Now one more important point is that maximum internal developed torque is also referred as stalling torque, pull out torque or breakdown torque. All are having the same meaning. Maximum torque, stalling torque, pull out torque or breakdown torque. So this is the slip corresponding to the maximum developed power, means whenever the PGMD is maximum, so at that point of time what is the slip value? So your slip value at that time will be equal to R2 dash upon R2 dash plus, just a second, root over RTH plus R2 dash whole square plus XTH plus X2 dash whole square. All right. So this R2 dash is 1 by S minus 1. This is equal to RTH plus R2 dash plus XTH plus X2 dash. Okay, so all right. Now this PGMD, this is equal to what? This is equal to the maximum power that we are getting. So this is equal to 3 times of R2 square under PGMD into what is the electrical parameter which denote the gross mechanical developed power. R2 by S is the rotor, is the equivalent parameter for the rotor input, and R2 dash 1 by S minus 1 will give you the mechanical developed power. So the 3 into I2 square PGMD will be into R2 dash 1 by S minus 1. So this component, this resistor will give you the actual power of the gross mechanical developing. All right. So let us move ahead. Maximum torque, maximum slip torque, starting torque and maximum torque, by using the approximate analysis. And my dear friend, 99.9% of time, 99.9% of time, you will going to use the approximate analysis. All right, during the exam, in whatever question you are supposed to be get in the GATE exam, that will be from the approximate analysis. Sir, what is approximate analysis? Approximate analysis, it means that your stator impedance will be zero. Means the resistance of the stator, leakage reactance of the stator will be zero. So I have ignored the impedance of the stator. At the same time, I have also ignored the core loss of the induction machine. Now, once you do so, your your RTH will become 0, XTH will become 0, and VTH will become equal to V1. Done. So, put these all values in RTH, XTH and VTH. You will get RTH 0, XTH 0 and VTH equal to V1. Now, with all this value, your SM, see here, this is the exact value na. So, RTH and XTH will be 0. So, from here you will get R2 dash by X2. So, here this is R2 dash by X2 dash, or this is also equal to R2 by X2. Next, the torque equation, which is 3 by omega S into VTH square, means V1 square upon R2 dash by S whole square plus X2 dash square into R2 dash by S. Done. Now, starting means, the starting torque means slip value will be 1. So, put S value equal to 1 here. You will get the starting torque 3 by omega S into V1 square whole divided by R2 dash square plus X2 dash square into R2 dash. And the maximum torque means replace R2 dash by SM. Replace R2 dash by SM here with X2. You will get 3 by omega S into V1 square upon 2 times of X2 dash. So, your maximum torque is independent of the rotor resistance, because we are not having the resistance here in the expression, and your the slip at which this maximum torque is occurring is depend on the rotor resistance, but maximum torque does not depend on the rotor resistance. So, let us move ahead. This is the torque slip characteristics of the induction motor, where this region is known as motoring region, where slip is between 0 to 1, and where the slip is negative, means S less than 0, is known as generating mode. So, here induction motor will work as an induction generator, and when the slip is greater than 1, your induction motor will work in the region which is known as breakdown region, or you can say that pledging region. All right, okay, यहाँ पे लिखा हुआ है, that is braking mode. Am I clear? So, have a look over the torque slip characteristic. So, I will going to discuss only this part. So, because we are interested in the motoring mode. So, in the motoring mode, slip will be 0 to 1, where this point is the starting torque. Where slip value will be 1, and this point is your slip corresponds to 0, means your rotor speed will become synchronous speed at this point. Done. The torque which is occurring as a maximum at that point of time, the slip will be S max, which is SM. That we have written SM or SMT, I think we have written. All are same. SM, which is equal to SMT, all are same. And the torque corresponding to that point is T maximum. All right. Now see, this portion between SMT to 0, between SMT to 0 is known as stable region or linear region, because here torque, electromagnetic torque is proportional to slip. All right, and the region between 0 to S max is known as, this region is known as unstable region or hyperbolic region, because here torque or electromagnetic torque is proportional to 1 by S. All right. So starting method of the three-phase induction motor. So what do you mean by starting method? Means to start the induction motor. Is it so? No. The three-phase induction motor is a self-starting motor. Means there is we did not have to adopt any kind of device such that the induction motor will going to be start, because the induction motor itself is a self-starting machine. So what is the meaning of starting then? The meaning of starting here is that at the time of starting, the impedance in the induction machine is very, very low or very, very small. So if the impedance is small, then the current corresponding to that impedance will be high. See here, at the time of starting, slip is 1, then your R2 dash 1 by S minus 1. This value will be what? This value will be 0. Ignore this one, ignore this part. Ignore this part. For the analysis purpose, so that analysis become easy, we need to ignore this part. Okay, by ignoring this part, we will analyze the circuit. So once you put S equal to 1, this will going to be short circuit, isn't it? So your ZSC means the impedance from here will be equal to what? R1, this value, plus R2 dash plus JX1 plus JX2 dash. And this value is nearly equal to, in terms of magnitude, nearly equal to 1, or in the rare case, or to be precise, it is less than 1. So your current, which is I1, which is equal to I1 dash, if you ignore this part, which is equal to I2 dash, will be equal to V1 divided by ZSC. So see, if ZSC is less, then the current at the time of starting will be very, very high. If such current will flow in the machine, the winding will going to be damaged. So for that we need to adopt some techniques so that we can limit the current at the time of starting. But at the same time, since the torque depend on the current, the torque or the starting torque should not decrease to some extent. All right. So we have a 4 method, in which the first one is direct online method, which says that at the time of starting, the voltage that you will going to be apply here is rated voltage, V1 rated. Or if I write V1, this means that we are giving the rated voltage here. Now direct online means you are connecting the induction motor directly to the supply lines without stepping down the voltage. So here I starting will be equal to what? V1 divided by ZSC. Now if you give the, please listen me very carefully, when you give the rated voltage here, then your starting current is known as short circuit current. So if this is rated, then your IST is known as, or is termed as, short circuit current, and this current is very, very high. All right, but anyway it is understood that here V1 is the V rated, so your IST is basically equal to ISC. All right, and the starting torque divided by full load torque, here this is equal to IST by IFL whole square into SFL. And here IST is ISC by IFL whole square into SFL. Next, stator resistance or reactance starting means what we are doing. This is the line voltage and we are decreasing the voltage to some value, let us say some X value here, and this voltage, this X voltage we are giving to the stator. Here X is less than 1. So this is basically a kind of potential divider. Alright, this is a kind of potential divider where we are not giving the full voltage, rather we are stepping down the voltage to the value X, and after that we are giving this value. Alright, so the line to line after this √3 X times of V1. So this is line voltage. What will be the per phase? What will be the per phase given to the stator? My dear friend, this part is the potential divider circuit, and this is your induction machine. This part is stator and this part is the rotor. So the voltage per phase that you are giving at the stator will be what? X times of V1. Considering the star connected system, X times of V1. So your IST means here the current which is entering will be equal to X times of V1 divided by ZSC. Alright, so this is equal to X times of ISC. V1 by ISC. V1 is the rated voltage. So your starting current will be this X times of ISC in this method, and the starting torque divided by full load torque, this is equal to X square ISC by IFL whole square into SFL. So this two formula is important in this method. Let us move ahead. Here this is √3 V1. So here we have connected one auto transformer, and this is your induction motor. Alright, so in this case the supply current I supply, this is equal to X square times of ISC. X square times of ISC, where IST is what? X times of ISC. And your starting torque divided by full load torque, this is equal to X square ISC by IFL whole square into SFL. Okay, so this is the auto transformer and this part is your induction motor. Next is the star delta transformer. In the star delta transformer, your starting current by the full load current, you can say, or sorry, not a full load current, starting current by ISC, this is equal to 1 by 3, is equal to 1 by 3, and starting torque divided by full load torque, this is equal to 1 by 3 times of IST by IFL whole square into SFL. These three formulas are very means this three method formula are very important. The auto transformer, the stator resistance formulas, and the star delta formula. These 6 formulas very important for the GATE question. Now let us move ahead with the single phase induction motor. So when you convert the 3 phase to the single phase, it will become the single phase induction motor. So this is the starting method. Here the single phase induction motor is not a self-starting motor. So for that particular reason, we need to adopt some technique to make the single phase induction motor to get started. So in which we have a 4 method, we will going to deal only 2 because 3 and 4 will have the same formula as that of 2. Alright. So in the resistance, what we will going to have, this resistance, where this resistance, or you can say the auxiliary winding. Due to auxiliary winding, we need to make, with the help of auxiliary winding, we are making the induction motor to get the self started. But the starting torque to get the maximum, the torque to get the maximum, what should be the condition? The condition is that your torque, which is proportional to I auxiliary, I main, and sine of angle between IA and IM. This is the electromagnetic torque in the induction motor, which is proportional to IIM sine of angle IA and IM. So see, this value is maximum when this angle will be 90 degree. So I need to choose such values such that this angle will become 90. So how we will going to do that? Phi m means this angle plus this angle, auxiliary winding angle, should be equal to 90 degree. So tan inverse xm by rm plus tan inverse xa by ra should be equal to 90 degree, such that this part will become maximum, which is sine 90 degree will be 1. Now here we are placing a capacitor in series with the auxiliary winding. In series with the auxiliary winding, we will be having a rotor here. So what will be the XC value such that the angle will become 90 degree? The value will be like this. XC is equal to XA plus RA RM by XM. Try to remember this formula. This formula is very, very important. Okay, where XC is 1 upon omega. Done. And the condition for the maximum starting torque means, if you look at the formula, your electromagnetic torque depend on IA, IM, and sine angle between IA and IM. So by using the technique that we have discussed, we have made the angle 90 degree. But my friend, you are forgetting that your torque is also depend on IA and IM. So until and unless IA and IM will be maximum, you cannot able to get the starting maximum, or you can say maximum starting torque. You cannot able to get. So how to or what will be the condition such that your torque will going to be maximum at the time of starting? So the condition is that phi m plus 2 times of phi a should be equal to 90 degree. Just a second. Okay, so this will be the condition. Very important condition. If you give or if you make phi m plus 2 phi equal to 90 degree, then the torque which you are getting in the single phase induction machine will be maximum at the time of starting. So with this we have completed all the formulas which are important from the transformer and the induction machine. All right, and the induction machine. So we will going to take a break of a 10 minute. All right, of a 10 minute. We will resume the class exactly at 7:25. Exactly at 7:25. So we will take a break over here, and we will resume, or we will meet after 7:25. So welcome back. So I hope you are enjoying this session of the electrical machine, isn't it? No. So we have completed our a two chapter, that is transformer and induction machine, and we have seen a lot of formulas related to those chapter. Now we are going to enter into the two chapters which is only for the electrical stream, not for the IN. For the IN stream we have already covered. So this particular session is especially dedicated for the double E stream. All right. So shall we start? Double E soldiers, shall we start? Okay. So this is a DC machine in which the weightage for the double E will be between 2 to 4 marks, and in that the important topic is, I have written over here, so you can pause and read the important topics. Let us directly jump into the formula. So the EMF and the torque equation in the DC machine is what? The EMF generated in the armature. Here EA is P phi NZ by 60A. So phi Z by 60 into P by A, where P by A, see here, P by A, Z upon 2 pi will be constant. So how I have written this? Sorry. This is what? This is equal to P phi NZ by 60A, and omega is, or you can say omega m, here is 2 pi. Okay, that I have already written here. Omega m is 2 pi n by 60. So replace n with 60 into omega m upon 2 pi. So you will get K, which is equal to Pz upon 2 pi A, constant of the machine. All right. So EA will be equal to K phi omega m. This formula is very important. Means whatever formula that we are supposed to use for the DC machine is one of that formula is of EMF equation. All right. Until and unless you know this formula, you cannot able to solve the numerical question related to the DC machine. So this formula is very important, where phi is flux per pole, P is number of poles, Z is number of conductor, A is A is number of parallel paths, which is equal to P for the lap winding and equal to 2 for the wave winding. All right. So try to remember this part, lap winding and wave winding. N is speed of armature in RPM, and omega m, N is what? This N is speed in RPM, all right, revolution per minute, whereas omega m is the mechanical speed in terms of radian per second. All right. So try to remember the difference between capital M and omega m. So the next formula that we are going to have is the torque equation. So as we know that in a machine, P developed is equal to torque into omega R. P developed is what? This is the electrical power. If you are talking about the a generator or a motor, in all the cases the P developed in terms of electrical power will be equal to armature voltage into armature current. And when you divide with omega R, you will going to get the torque, isn't it? The omega R is the armature speed. Nice summarization of the topic, sir. Thank you, Amit. So omega R is the speed of the armature in radian per second, which we usually named as omega m in DC machine. Am I clear? Where T is torque developed in Newton meter and IA is the armature current. Now this is the circuit model, or you can say the one of the important model in the DC machine is this one. All right, which is known as a DC shunt machine. Now the first diagram is of the DC shunt generator and the second diagram is of DC shunt motor. All right. So how to know that from the circuit that the machine will be a generator or a motor by seeing this load current diagram or a terminal current diagram. If the current is entering into the load, it will behave as a generator, and if the current is coming from the terminal, will be known as a motor. Okay, so this part is a terminal where the electrical component will going to be connected or the grid will going to be connected. So here IA is equal to, if you apply the KVL here, you will going to get IF, this is RF, here this is RF, IA equal to IF plus IL. Okay, what else? VT will be equal to EA, this is EA, comma RA, EA minus IA RA minus brush drop. Next, IF will be equal to VT by RF. So VT is known as terminal voltage here. Next, in the motor, your IA is equal to IL minus IF, and VT is equal to EA plus IA RA plus brush drop. This drop, this is a brush. Okay, and the last one is IF, this is equal to VT upon RF. So in both the machine, the formula for IF will be same. The two formula will going to be changed, which is of IA and VT. Am I clear, everybody? Next, this is a power flow in the DC generator. So for the DC generator, not a DC generator, this is a DC motor. Okay, this is a DC motor. Just a second. This is DC motor. All right. Okay. Now in the DC motor, what we have? We have input as a electrical and output as a mechanical. So see here, your input power will be VT into IL and output will be the mechanical, which is torque into omega. So in between these two, I'll be having the rotor and stator. So we have a ohmic loss, which is a copper loss, you can say. IA square RA will be equal to ISH into RSH. I hope this is not visible to you. This is IA square RA loss, ISH square RSH loss, I square AC RAC loss, and VBD IA. These all losses are known as ohmic loss or a copper loss. So once you subtract these losses with the input power, you will get the air gap power. Okay, the power which is flowing through the air gap is air gap power, which is equal to EAIA. This is EAIA is equal to electromagnetic torque into omega. So the formula that we have derived here, na, this is the electromagnetic torque, which is T or TE, you can say. This can be written as TE. This can also be written as TEM or simply T. Okay. Now after that, we will be having a shaft, and at the shaft we will have a rotational losses, which is a combination of frictional and windage loss. All right. And after deducting these losses with this, you will get the output power. Next, the efficiency formula. So efficiency is what in the machine? Efficiency is 1 minus losses upon input power, or you can say output upon input power, or output upon output power plus losses. These all three formulas are same. Now in the DC generator, your efficiency is known as NG, which is equal to output power divided by output power plus losses, and in the generator what is output power? Output power is the electrical power, which is terminal voltage into line current IL, all right, and divided by VT into IL plus this all losses I square R plus constant losses plus brush drop. Okay, so please do not consider in this, please do not consider a brush drop losses, because I have written that brush drop losses separately, or I think it is better to keep here only. Okay, it is better to keep in the ohmic loss itself, all right, into 100%. So this is percentage Ng formula. So try to remember this formula. This formula will going to help you in the GATE exam while solving the GATE question, because if you are not able to understand the notation, means what notation implies in the machine, then my dear friend, you are going to be in a big trouble, all right. So try to remember this formula. Let us come to the DC motor, where Nm is input power minus losses upon input power. What is input power in the motor? Electrical power. So can I write this as 1 minus total losses, which is equal to I square R loss plus constant loss. Let me see. I square R loss and constant loss divided by input power. Input power is electrical in the motor, which is Vt into IL into 100%. Now some point to be noted down here is that for generator and motor, maximum efficiency occurs when constant loss is equal to variable losses. So when I square R become equal to PC, not this one, when I square R become equal to PC, means whenever okay, this should be variable loss equal to constant loss. Then you will going to have the maximum efficiency, and for maximum power output, my dear friend, these two are different. In the first we are getting the maximum efficiency, and in the second we are getting the maximum output. So for maximum output by DC motor obtained when EA equal to V by 2 and IA equal to V by 2 RA. Okay, EA equal to V by 2, this is the condition, and current IA equal to V by 2 RA. So when your EA becomes equal to V by 2, you will going to get the maximum output, and at the maximum output condition you will be having the efficiency at 50%. So whenever you are going to draw the maximum power, then your efficiency will become 50%. Maximum power does not implies that you are going to get the maximum efficiency. It is not that kind, all right. So at maximum power you will going to get the 50% efficiency. Now the speed control of DC motor, the omega m depends on Vt minus IaRa divided by Km phi. How, sir? This is basically EA, na? EA equal to Km phi omega m. Alright, so this we have written at the starting of this slide. Alright, so EA K phi omega m. So from omega m, this is equal to Vt minus IaRa by Km phi. So EA is Vt minus IaRa. So from here you can say that omega m depends on terminal voltage, armature current, armature resistance upon Km constant, and phi is the flux. Now here omega m basically depends on the 3 parameter, not the 5 parameter. Why, sir? Km is anyway constant, so you cannot able to control the speed. And Ia, this Ia depends on the load, means what load you are connecting to the machine. So basically this Ia is a function of the load, so that itself is also not going to be the control parameter. So you are left with Vt Ra and phi. So this is the reason we have three controlled method: armature voltage control, armature resistance control. Armature voltage matlab Vt, armature resistance control means Ra control, and field flux control matlab ki phi. All right. So in this segment, the first control is armature resistance control, and the machine that I am going to take is the DC shunt motor. Please do not ask me, sir, why you have not taken DC generator. My dear bacha, I am controlling the speed, na. So the speed is what? Mechanical, and the output in mechanical will be for the motor. Am I clear? So let me change the color. Okay. Now see here, this is the DC shunt motor, where the first part is the armature, the second part is your shunt resistance, and this is terminal voltage Vt, this is armature resistance Ra, and we are controlling with respect to armature resistance, na. So we are adding one external resistance as Rg. External resistance as Rg. So with this external resistance, I am going to control my speed, and here we will be having a back EMF, or you can say the EMF, and this is shunt resistance, which is RSH. Now, what type of load we are connecting? You will going to get the different kind of equation. Means depending on the type of load, you will be having a different sort of equation. So basically, in the question, we will be going to given any of the two torques, whether the load torque will going to be constant or load torque will be proportional to the N square. This type of load are termed as a lathe machine kind of load, and this type of load, where load depends on the speed of a square, is of fan type. Okay. Here, this is the example of this torque is a lathe machine. All right. Now here, in the examination, you are supposed to calculate the armature current, or you can also supposed to calculate the new speed, means the new armature current or the new speed of the motor. So basically, under steady state, your electromagnetic torque will be equal to load torque, and electromagnetic torque is what? Km phi Ia. This we have seen, Km phi Ia. This is, since the load torque is constant, so let me write here constant. Now, in the shunt machine, we are not changing this RSH, and Vt is anyway constant. So Vt by RSH is what? Give you ISH, which is If, and your flux is proportional to If. Let me see whether this is visible or not. Okay, this is visible. So when If is constant, the flux is constant. If the flux is constant, can I say your Ia will be constant? So your Ia2 is equal to Ia1, or this is the generalized formula that I have written. If your load torque does not depend on the speed, that is the speed is constant, then this function of N2 by function of N1 will be equal, and from here you will get Na2 by Na1. So I have generalized the expression as function of N2 by function of N1. Am I clear? But if TL is constant, your Ia2 will be become equal to Ia1, and next you are going to use the second equation, which is Ea, which is proportional to phi into N. See here. Okay, where should I write? Okay, let me write here. Your Ea is what? Ea is Km phi omega m, and omega m is what? 2 pi n by 60. So this km, phi and 2 pi by 60 is constant. So can I say your EA is proportional to n? Your EA is proportional to n. So this part is equal to n. So Vt minus Ia2 Ra plus Rg means when you have introduced this resistance, then at that time armature current, this Ia, will going to change. So Vt minus Ia2 Ra plus Rg, the EMF across this motor, will be this one divided by Vt minus Ia Ra when you have not introduced this Rg, will be equal to N2 by N1. So by using these two formula, you can able to find N2 or Ia2. Means one of the values will be provided to you in the question. Either Ia2 they will provide, then you are supposed to calculate N2, or N2 they will provide and you are asked to calculate Ia2. Am I clear? Now, when the load torque is proportional to n square. Now see here everybody, please look at the board. When load torque is proportional to n square, then your electromagnetic torque under steady state will be equal to TL, and for the shunt machine your T is Km phi Ia, and this is equal to, removing this proportionality sign, I can write this as K1 n square, isn't it? So where Km, phi and K1 all are constant, so Ia is proportional to n square. So see here, your Ia is function of N2, isn't it? Your Ia is function of N2. So Ia2 for the second case, Ia1 for the first case will be equal to N2 by N1 whole square. And the next equation you will going to get from here, Vt minus Ia2 Ra plus Rg whole divided by Vt minus Ia1 into Ra. This is equal to N2 by N1. So when the load torque is constant, you will be having this equation, the first equation, and this second equation. For getting the speed or the armature current, or you can say that the question related to the speed control, you would be requiring only two equation. The first equation will be the torque wala, this, and the second equation will be the EMF wala. So by using by the help of these two equation, you will going to find your unknown quantities. Am I clear? Let us move ahead with the DC series motor. So see, this is the DC series machine in which for controlling the speed I have introduced one resistor which is Rg, and this is terminal voltage Vt, and this is series current IAC, which is also equal to armature current and which is also equal to line current. In the series machine, line current, armature current, series current, or you can say field current, all are same. Done. This is RSE and this is armature resistance Ra, and here back EMF EA. Now again we need to see what type of load that we have given. If the load is constant, then your TE, which is equal to constant, under steady state TE will be equal to TL, na? And what is TE? TE is Km phi Ia, this is equal to TL. But my dear friend, in series machine, see, your flux will be generated by this series field winding, and this series field winding is what? Having the armature current Ia itself. So can I say your flux, is this visible? No, just a second. Your flux is proportional to Ia here, your flux is proportional to Ia here, because armature current is flowing through the series resistance. So when you substitute flux in this equation, you will going to get Ia square equal to constant. Ia square equal to constant. So Ia2 by Ia1 whole square equal to function of speed. So here speed is constant, means your load torque does not depend on the speed. So your load torque is constant. This means that your speed here will not means here armature current will not depend on the speed. So can I say this ratio will going to be constant? So particularly for this kind of load, your Ia2 will be equal to Ia1. Again, this equation is Ea proportional Ea equal to Km phi omega m, Km phi omega m. So here Vt minus Ia2 Ra plus Rac plus Rg upon Vt minus Ia1 Ra plus Rac equal to Ia2 by Ia1 into N2 by N1. All right. So this is the component we are getting from the flux, isn't it? Km phi n, Km is constant. So this is the Ia2 which give the flux for the case 2, and Ia1 will give the flux for the case 1, and these two fluxes depend on the armature current. This is Ia1. Next, when the load torque is equal to n square. So with this, can I say Ia square is proportional to n square due to function. So from here Ia2 by Ia1 will be equal to N2 by N1, and this is the one equation which we get from the torque, and the one equation we will going to get from this EMF wala. So right here you will going to have two formulas, and from there you can calculate N2 or Ia2. Now the flux control, here we are changing, or we are controlling the speed by controlling the flux, So here the flux is basically controlled by this parameter, the shunt, in the shunt motor. So this is your Rg, just a second, this is your Rg, this is Rsh, this is Ra, this is Ea, and this is Vt. This is line current IL, armature current, and this is shunt current. All right. Now see here, your ISH is now not constant. Once you introduce this Rg, and by varying this Rg, the ISH will going to be changed. This means that the flux will not going to be constant for this control. Now, what we can do here? See, your electromagnetic torque here is constant, and electromagnetic torque is what? Km phi Ia, which is again constant, Now your flux is what? This flux is proportional to I shunt, and this I shunt is what? This is Vt upon Rsh plus Rg. Rsh plus Rg. Now look at here. Phi 2 Ia2 divided by phi 1 Ia1, which is equal to constant here, So phi 2 can I write? Vt upon Rsh plus Rg into Ia2. If you multiply here, Vt upon Rsh plus Rg into Ia2, divided by phi 1. Phi 1 is what? When you have not introduced this Rg, then phi 1 will be proportional to ISH1. So in that case, your flux will be equal to Vt upon Rsh. So this is Vt upon Rsh and into Ia1, and these things are constants. I hope you have got the point. Done. So this equation we are getting from the torque wala. Next equation is Ea proportional to phi into omega, phi into n, or this is proportional to IFN. So Vt minus Ia2 Ra for the second case when Rg was not introduced, divided by Vt minus Ia1 Ra when this case is for when Rg has been introduced, this case, and Vt minus Ia Ra, this is the case when Rg was not introduced. This is equal to If into N. So If is what? This is inversely proportional to the resistance. So for the case 2, and this is for case 1 into N2 by N1. Let me rub this. In this case, your phi 2 Ia2, phi Ia is proportional to N square. So can I say phi 2 Ia2 divided by phi 1 Ia1 is equal to N2 by N1 whole square. And what is phi 2 by phi 1? Is this value RSH upon RSH plus Rg into Ia2 upon Ia1. This is equal to N2 by N1 whole square. Just a second, N2 by N1 whole square. Okay, so this is the first equation. And what is the second equation? From here we are getting the second equation. Okay, so this is your second equation. This is your second equation. So you have two equation, you have two unknown, so you can find the unknown parameter. Next is flux control in the DC series motor. Now in this please do not introduce Rg in the series with Ra, because again it will become the armature resistance control. So what we can do, we can add a resistor in parallel with the series resistance. All right, in parallel with the series resistance, and with this resistance, which is R diverter, we can control the speed. This is terminal voltage Vt, this is motor, back EMF is Ea, armature resistance is Ra, this is series resistance Rac, this is armature current Ia, this is diverter current, this is series current, and this will give you armature current again. So again you will be having the two cases, either the load will constant or it will be proportional to N square. So when the load is constant, see here, when the load is constant, you will get this equation. For the constant load, this part will going to be equal to 1. So for that particular reason, this value numerator will become equal to the denominator. Am I clear? When the load torque is constant, this will going to be constant. And the second equation will be you will going to get from the EMF wala, where Vt minus Ia2 times Ra plus Rac parallel R div. Okay, RAC parallel R div, this resistance, upon VT minus IA1 RA plus RAC, this is equal to IA2 upon IA1 times R div divided by R div plus RAC into N2 by N1. So you have two unknown, you have two equation, you will going to get the answer. Now in this part, this equation will be proportional to N square, means IA2 square R div upon R div plus RSE whole divided by IA1 square, this is equal to N2 square by N1 square, because here load torque depend on the speed. Am I clear? Now the next equation is this one. So you have two equation, two unknown, you will going to have your answer. Now in this, again, this is known as armature voltage control, and this can be employed to the DC shunt type of motor. Am I clear? So this is armature voltage VT. This is the potential divider. Actually we are varying the armature voltage, and this voltage across the armature is known as armature voltage, isn't it? This VT is terminal voltage. So we are changing the armature voltage, not the terminal voltage. So how we will going to change the armature voltage? We will connect a resistor in parallel to this motor, and by varying this the jockey, you can say, or a variable resistor, we can vary the armature voltage. Am I clear? So this is RSH plus minus EA, and this is armature current, this is line current, and this is shunt current. So you are having these same two cases. Your IA2 upon IA1 will be function of N2 by N1. When load torque is constant, this will become IA2 equal to IA1 when load torque is constant, and this equation is due to EMF wala. EA is proportional to N. Because this is shunt machine, so flux will going to be constant here. And in this, your IA2 by IA1 will be equal to N2 by N1 whole square, and VT2 minus IA2 RA upon VT1 minus IA1 into RA, this is equal to N2 by N1. What is VT2 and what is VT1? The voltage by varying this resistor. Suppose if this point, RA here. Suppose if this point is here, then your VT1 will be VT, and when this is shifting, when this variable resistor is here, at that particular point, the terminal voltage will be VT2. I hope this point is clear to you. Okay, let me write here. Okay, this is IA, done. So with this, we have completed all the formulas which are important for the DC machine and considering to the GATE exam. Now let us come to the synchronous machine, in which the weightage will be same, and these are the important topics. Now the important concept in the synchronous machine, the electrical angle will be equal to P by 2 theta mechanical. Your angular frequency omega E equal to P by 2 times of angular speed omega m. So this is electrical speed, you can say, or angular speed. Let me change the color, just a second, let me change the color. Okay, so your NS is synchronous speed, which is 120 F by P. And here the synchronous speed is basically conversion of electrical frequency in mechanical speed. So this is a case for motor where electrical frequency is converting into speed, and the speed is relevant for the synchronous machine because the rotor of the synchronous machine rotates at the synchronous speed. Next point is synchronous generator is also known as alternator because it generates alternating voltage, or you can say the sinusoidal voltage, and synchronous generator generates power at fixed frequency. Now here if you see, your synchronous speed is basically conversion of the electrical frequency in mechanical speed. So this is for the motor. Now in the generator, your mechanical speed will going to be means in the generator, your mechanical speed will going to be converted into the electrical frequency. So both are analogous. Now induced EMF in the winding. So the EMF which are inducing at the stator will be given by EF, which is normally written as E. This is equal to 4.44 flux per pole into frequency into turns per phase. Since the synchronous generator or a motor is a three-phase machine, so this EMF, the formula that we have is for the per phase. Now if you are supposed to calculate the line voltage, then in star connection, your line voltage or induced voltage line will be equal to √3 times of EF. All right, and in delta connection, your line voltage is equal to phase voltage, which is EF. So this is per phase induced EMF. Okay. Now EMF in the short pitch winding. What do you mean by short pitch winding? Suppose you have a coil like this. I have taken 1 ton coin only for the simplicity. So if one end of the coil is under north pole and one end of the coil is under south pole, then this sort of coil is known as full pitch coil, and the angle between these two is always 180 degree electrical. All right. Now when this coil, let us take this as north and this as south. Now when this coil are not under the pole, rather just a second, rather they are displaced by some amount of angle. Let us say this angle is equal to epsilon by 2, and from here also epsilon by 2. So the total displacement will be what? Total displacement will be epsilon. So the angle between the two coils will be 180 degree minus epsilon. If the total is 180 degree and it is shifted by an angle of epsilon, total angle epsilon, so the coil that it will going to take the angle or occupied the angle will be 180 degree minus epsilon. So see here, earlier A and A dash, okay. So this part is what? Basically A, this overall part, this is A, and this overall part is A dash. So when A is under north pole and A dash is under south pole, so the angle is what? 180 degree, and this is known as full pitch coil. But if it is displaced, suppose if A is here, the final position, and A dash will be here, displaced by an angle epsilon by 2, then this is known as short pitch coil, and the displacement will be with respect to angle E by 2. So in this case, the EMF equation will be, see here, your EMF equation will be 4.44 flux per pole, supply frequency, turns per phase. One terms you will going to multiply is Kp. And what is Kp? Kp is short pitch factor, which is equal to cos epsilon by 2. Now EMF for the sinusoidal flux distribution, so E for non-sinusoidal flux distribution, this will be equal to 4.44 phi flux per pole due to that particular nth harmonic into n times of f into turns per phase into Kpn into Kpn. What is Kpn here? Kpn will be equal to cos of n epsilon by 2. Now suppose you want to eliminate the third harmonic, then what should be the angle? You want to eliminate the third harmonic, then Kpn has to be 0. Then what will be the angle here? The epsilon value will be here. So for that, epsilon will be equal to pi by n. Equate this n epsilon by 2 with pi by 2, you will get epsilon as pi by n. So if you choose epsilon such that those frequency those harmonic will go, you want to be reduced. Thank you. Okay. Razang La. Thank you, GATE Academy. All right. So if you choose epsilons such that it will going to eliminate those particular nth harmonic. So the n, if you put the n as 3, suppose if you want to eliminate the third harmonic, your pi by n or you can say pi by 3 will be equal to 60 degree. Pi here is in radian, but if you want to find in terms of angle, then your pi radian is equal to 180 degree. So if you want to write in terms of angle, replace this pi with 180 degree, then for particular for that particular harmonic you will going to have this epsilon value. All right. So now let us know some terminology related to the distributed winding. So here the windings on the rotor are going to be distributed over the periphery. So due to that, we will having the some sort of terminology. So the first one is coil span. So this we have already seen. This part is known as beta. This is coil span, and this is also a beta. So depending upon the coil position, the beta will going to be having those value. So if it is 180 degree electrical or slot per pole, then the coil span is then this is full pitch coil. Full pitched coil. So either they will give a full pitch coil or they will give a short pitch coil. So from there we can judge that your beta will be 180 degree electrical or slot per pole. But if this is less than, if beta is less than 180 degree electrical or less than slot per pole, then this is known as short pitch coil. Done. Now pole pitch. Pole pitch is what? The angle between the north pole. The angle between the north pole and the south pole. So the angle between the north pole and south pole is always an electrical angle and is always equal to 180 degree in terms of electrical. And but if you want to know the formula, your theta electrical is equal to number of poles divided by 2 into theta mechanical. Done. Now slot angle gamma, this is equal to 180 degree upon slot per pole, and this value is in mechanical angle or electrical angle. always in electrical angle. Done. Next, phase belt. What is phase belt? Means what amount of slots are taken by the particular type of phases. So this is equal to number of slots per pole divided by per phase. Next, phase spread means what amount of angle are taken by those particular phases. So this is equal to m gamma. So from gamma we can get from here, and m we can get from here. All right. Next is EMF in the distributed winding. So this is equal to 4 point, or you can say E distributed. This is equal to 4.44 pi F turns per phase into KD, where KD is distribution factor, and this is given by sine m gamma by 2 divided by m sine gamma by 2. Again, the most important formula. Now, if you want to eliminate the nth harmonic, then sine m n gamma by 2 must be equal to sine pi. Or from here I can say that your gamma means the gamma should be such that 2 pi by, it will become 2 pi by mn. Okay, if you want to eliminate the particular harmonic, then gamma should be such that it will become equal to 2 pi by mn. Next is uniformly distributed winding. So uniformly distributed winding means what? When gamma, condition is that means condition such that the machine is referred as, or the winding is referred as uniformly distributed winding. The condition is that your gamma is equal to 180 degree, which is slot per pole in terms of electrical. This should be less than equal to, this should be less than 15 degree. So whenever gamma is less than 50 degree, 15 degree, then it is known as uniformly distributed winding. So in that case, your E distributed winding formula will going to be changed. How? 4.44, this is equal to, just a second, okay, 4.44 pi F turns per phase into KDU, distributed uniformly. U means uniformly. So your KDU will be equal to sine m gamma by 2 upon m into gamma by 2. Gamma by 2. This is angle, na? This is angle. So convert it into radian by multiplying pi by 180 degree. Means we have approximated here. We have approximated sine gamma by 2 as gamma by 2. So this is degree. This is gamma by 2. So this approximation is only valid if gamma is less than 15. So you need to convert this angle into a radian by multiplying pi by 180. Next, this is the armature reaction concept, where the effect of armature flux phi A on main field flux phi m is known as armature reaction. And armature reaction depends upon the magnitude of the load and the load power factor. So depending upon the power factor and depending upon the machine, the armature reaction will going to have this kind of nature. So for the unity power factor and alternator, your purely cross magnetizing flux will going to be happen, or the armature reaction will be purely cross magnetizing. And for the motor, you will also having the same nature, which is purely cross magnetizing. For the zero power factor leg, it will be purely demagnetizing in case of alternator, and in case of motor it will be purely magnetizing, and so on and so forth. So have a look for the natures of the armature reaction. All right, so equivalent circuit for the cylindrical rotor synchronous generator. So this is a generator, cylindrical type of rotor, where EF is the induced EMF, VT is the terminal voltage, and this RA and J axis, sorry, RA and J axis. This is known as synchronous impedance, which is equal to ZS equal to magnitude of ZS at an angle theta s in terms of polar. And this is current IA, armature current IA. Done. So from here I can write EF is equal to VT plus IA times ZS. This is ZS. No? Next, the phasor diagram. All right. So by considering the load to be lagging type, by considering the load, okay. One more thing. Let us write this equation in terms of their magnitude and phase angle. So here EF will be written as EF at an angle del. So my dear friend, EF here is what? Magnitude. Okay, please do not consider this as a phasor. Here EF, this EF is a magnitude at an angle del. Taking this as a reference, magnitude of VT at an angle 0 plus magnitude of IA, magnitude of ZS at an angle. Let us take the power factor as phi, power factor as phi, and this angle as theta s plus theta s. So if the load is a lagging type of load, then this phi will be negative, and if the load is leading type of load, this phi will be positive. Now if you draw the vector diagram by considering the load to be a lagging type, then the angle between VT and IA is known as load power factor, which is phi, just a second, which is phi, and the angle between EF and IA is known as internal power factor angle, because EF is the internal part of the machine. So this is the reason why EF and IA angle is known as internal power factor angle, and the angle between EF and VT are known as load angle, which is del. And where is IISz? IISz will be just a second. IISz will be this value. Okay, so this is IISz, and this angle is what? Theta. This is VT, IARA, ISXS, and hypotenuse will be ISZS. So VT plus ISZS will give you EMF, and the angle between this IARA and ISZS is theta s. All right, so here equivalent circuit. Now let us come to the synchronous motor. This is the equivalent circuit. In the motor, the input will be electrical and output will be your mechanical. So here EF vector will be equal to VT vector minus IA vector ZS. In terms of polar, it can be written as EF at an angle minus del. In the generator, del will be written in terms of positive angle, and in terms of in case of motor, your del will be written as minus del. This is equal to, taking Vt as a reference, so Vt at an angle 0 minus Ia Zs at an angle phi plus theta s. Okay, phi plus theta s. These all formulas are on per phase value. Please do not consider this as a line value. Whatever electrical or you can say the equivalent circuit are given to you are always drawn for the per phase. All right. And this is your phasor diagram. Again, this angle is the power factor angle phi. The angle between EF and IA is psi, and angle between EF and VT is del, and this angle minus IA Zs. So this angle is what? Basically theta s. This angle is basically theta s. Just a second. All right. Now, depending on the generator and motor, I have noted down some formulas which are important for solving the gate problem. Is that in case of generator, EF leads the VT by del, that we know. In case of motor, EF lags VT by an angle del, that we know. Means we have written a minus del. Now, EMF in magnitude is equal to Vt cos phi plus Ia Ra whole square plus Vt sin phi plus Ia xs whole square whole under root. Tan psi is Vt sin phi plus Ia Ra, means the second term divided by first term. And psi is equal to del plus phi. Now, my dear friend, this formula has been derived by considering the load as a lagging, isn't it? We have drawn the phasor diagram for the lagging type of load. So, this formula has been derived by considering the lagging type of load. What if the load is leading? If the load is leading, then replace phi with negative value. Suppose the machine is generator and you have derived the formula, this formula for the lagging type of load, and in the question they are asking the EMF for the leading type of load, then we can directly use the same formula. How? The current will be same. In case of generator, the current will be same, means the direction of the current will be from EF to VT only. So, armature current in both the cases will be positive. Now, let us assume that the power factor angle 0.8 is given to you. Then for the lag, power factor angle will be positive 36.86 degree, and if the power factor angle is leading 0.8 lead, then phi should be minus 36.86. So what you need to do? You need to put phi as minus 36.86 degree in the same formula for leading type of load. Now, suppose if you want to use the same formula for the generator, for the motor. We already seen for the generator now. Now, if you want to use the same formula for the motor, then what we can do? First, we have to reverse the direction of the armature current, because in the motor the current will flow from the VT to EF. So, IA will be reversed. So, minus 25, isn't it? The current will be reversed. And for the lagging, the angle will have to take the positive, as we are doing for the generator, and for the leading, we have to take the power factor angle as negative. Means the same generator formula, leading load, we can directly use in the other three cases. With this one, in this, just a second. in this, in this, and in this. All right. Now, one more important formula is magnitude of, let me rub this part. Magnitude of ISZS is equal to root over EF square plus VT square minus 2 EF VT cos del. This formula is very, very important. If you are not able to solve by using, means if you are not able to getting the answer with the above formulas, then definitely you should come to the sixth one. All right. So all these values are in the per phase, or whatever values we have for VF, VT, EF, all are the per phase value. And here the sign should be substituted with the value of the psi should be substituted with the sign. Means if the sign you are getting here, if you are getting here, suppose this is coming out to be minus 45, then from here psi will come, sorry, minus 45 not. Suppose this is coming out to as minus 1, then this implies your psi will be minus 45. So in the same formula, in this formula, whatever sign with the psi is coming, you have to be put with the same value. Am I clear? If you are getting plus 45, write plus 45. If you are getting minus 45, write here minus 45. Please do not convert into magnitude. Otherwise, you will going to have the wrong answer. Am I clear? So let me rub this part. Now the voltage regulation. What is voltage regulation? That we have seen in the transformer as well. So voltage regulation is equal to magnitude of EMF, that is EF, minus magnitude of VT divided by magnitude of VT. This is in per unit value. If you want this in percentage, multiply with 100. But here condition is that power factor, frequency and speed all has to be constant. Next, condition for the maximum voltage regulation. So condition that we have seen in the transformer itself, the same formula or the condition with that we are going to have. Your power factor phi will be equal to theta s. And what is theta s? Theta s is equal to, let me write here, your theta s is equal to tan inverse XS by RA. This is known as internal impedance angle of the synchronous machine. Now the maximum voltage regulation in terms of per unit, this is equal to at any fraction of load times Z in per unit. Now maximum voltage regulation, I think that we have calculated now. Okay, so just a second. Let me bring here. This is the maximum voltage regulation. And this is the condition. This is the condition. This is phi power factor. Next is condition for zero voltage regulation. So voltage regulation 0 means we are equal to 0 anyway. Now when we are getting this, we are getting this for cos of theta plus phi s. In the transformer, this theta plus phi is what? 90 degree. But in case of synchronous machine, this is equal to minus IA ZS 2 times of VT per phase. Okay, VT per phase. This IA is per phase, ZS is per phase, 2 times of VT per phase. Please do not forget to write this negative sign. Okay, this negative sign. Next is short circuit ratio. So SCR is defined as the ratio of field current required to produce the rated voltage on the open circuit to the field current required to produce the rated armature current on the short circuit. So this is basically the field current required to get the rated voltage on open circuit condition and the field current required to get the rated current under the short circuit condition. So these are the method which from where we can calculate the voltage regulation. The first method is synchronous impedance method, which is also known as EMF method. Second one is MMF method, which is also known as ampere turns method. The third one is ZPF method, which is zero power factor method. And the next method is ASA method. All right, American Standard Association method, ASA method. Now here, one thing is very important, means you can directly get, you may get directly question from the voltage regulation. Here voltage regulation in terms of descending order, means the voltage regulation due to EMF method here is higher, and later to that the voltage regulation is decreasing. Suppose if due to EMF method we are getting voltage regulation as 20%, then with ASA we are getting less than 20, with ZPF we are getting less than 15, and with MMF we are getting less than 5. Means these are the random value I have taken. So this is the reason why this EMF method is known as pessimistic method, matlab kharab method, and MMF method is known as optimistic method. Now the power angle equation of the alternator. So here this is the alternator, this is the alternator, or you can say that the synchronous generator, and this is the EMF, and this is the terminal voltage where you can connect the load, and the current which is flowing here is armature current, which is IA, and this is magnitude of ZS at an angle theta S. Magnitude of ZS at an angle theta S. So output power means here this output power, this is equal to, see here this output power, let me write here itself, your output power is equal to the voltage at the output terminal is VT vector into current entering at the terminal is IA vector, but conjugate, take a conjugate, because we are finding the complex power na. Now when you solve this, means when you find this IA, you will get this formula, P out equal to EF VT by ZS, this is into, not equal to, into cos theta S minus del minus VT square by ZS cos theta S. All values are in per phase, all values are in per phase. Note, all values are in per phase. Okay, and Q out, when you solve this, means replace IA here. From here, can I write IA as EF at an angle del minus VT at an angle 0 whole divided by magnitude of ZS at an angle theta S. So substitute this part here, you will going to get P out, that is output real power, output reactive power. P developed is what? This is equal to EMF at the rotor side, this is equal to EF at an angle, EF at an angle del into current coming from this rotor, which is equal to IA current na. So IA vector conjugate, IA vector conjugate, or simply we can write in terms of vector, this is equal to EF vector. So substitute EA here, you will going to get P developed and Q developed. Next, the power angle equation for the maximum power output, maximum power output. So why this is coming? Okay, please ignore this part. So maximum power output, what do you mean by this? To get the maximum power output, your theta, or you can say your del, should be equal to theta s. This is the condition. This is the condition to get the maximum output. See here, when theta s will or when del become theta s, so your P out will be maximum, because this part will become cos theta s minus del will become 1. So in that case, your P out will be maximum, isn't it? Now if this is 0, this difference is 0, then Q out will become minus Vt square by Zs sin theta s, minus Vt square by Zs sin theta s, and this is negative. And this is practically not possible, because if Q out is negative, see the direction. See the direction. Here your P out is in this direction and Q out is also in the same direction. So negative means what? The reactive power is flowing from the load to the source, which is practically not possible, because the load has to be a capacitive load. Next, stable operation condition means at what point of or at what angle the synchronous machine will lose its synchronism, which is known as synchronous stability. So when P out the change in output by the change in angle, if it is positive, then your steady state stability is happening and your system is under the stable condition, and the condition is that theta must be less than, sorry, not theta, del must be less than theta s. If this condition is fulfilling, your synchronous machine is working in a stable condition. So here when del is less than theta s, output power is less than maximum power. When theta is equal to del, output power equal to maximum power, which is also known as marginal stability of the system. And when del is, which is load angle, when del is greater than theta s, means output power is greater than maximum power, then your system is said to be unstable. Am I clear? मतलब ये कुछ इस तरीके से है कि आपके पास एक let us say polythene है, and in that polythene the capacity that it can hold is up to 20 kg. That is the maximum. And if you are try to give the or if you try to put the more weight in that particular bag, let us say if you are giving 21 kg, then definitely there are chances that your plastic bag will going to be teared out. So that 21 kg is what basically output that you are supposed to get, but the maximum that it can give is 20 kg. So this is the reason why it is said to be unstable. Try to remember this formula, this condition. This condition is very useful. Sometime you may get the directly theoretical type of question. Approximate equation. Approximate equation means your armature resistance Ra is much less than Xs, or Xs is much greater than synchronous reactance is much greater than armature resistance. So in that case, Zs is equal to Jxs, or in terms of polar, Xs at an angle 90 degree, which is magnitude of Zs at an angle theta s. So in the same formula, replace magnitude of Zs with Xs and theta s with 90 degree. So this part will become 0, isn't it? This part will become 0 and this part will become EF Vt by Xs cos 90 minus del is what? Sin del. So EF by Xs sin del. This formula you have often seen in the power system as well. So P out is EF Vt by Xs sin del, and similarly Q out you will get this formula, Vt by Xs EF cos del minus Vt, and P developed will be EF Vt by Xs sin del equal to P out, and Q developed will be EF by Xs EF minus Vt cos del. All right. Now one more thing, my friend here. See, your developed power is equal to output power, but your developed reactive power is not equal to output power. The reason is you have ignored the resistance which are supposed to be here. So if you have ignored this armature resistance, means there will be no copper loss. There will be no loss of the power. So if there is no loss in the circuit, then whatever power you are developing, that is a real. I am talking about the real power. The real power developed will be equal to the output real power. but due to reactance, the reactive component will not going to be equal. So the developed reactive power will be equal to the reactive power developed by due to this reactor and the power, the reactive power which are taken by the load. Next is power angle equation of the motor. So this is the power angle equation for the motor. Let me correct this one. Why this negative sign is come? Okay. So here again, this is IA vector, and in case of motor, the current is coming from the terminal to the into the machine. So here S develop will be equal to, let me write here, your S develop will be equal to, see here the S developed is generating inside the rotor, which is having the voltage EF vector, which is magnitude of EF at an angle minus del, into current, which is IA vector and conjugate. Done. And what is S input? See, the complex power entering into the machine is having the voltage VT vector into IA vector and conjugate. What is IA, my dear friend? IA here is VT at an angle 0 minus EF at an angle minus del whole divided by magnitude of ZS at an angle theta S. At an angle theta S. This is IA value. Next is maximum developed power. So again, dP max by d del, when you equate it to 0, you will get theta del equal to theta S. So in that case, P develop means the maximum power that it is developing is EF VT by ZS minus RA EF square by ZS, and Q develop will be negative from here. And the stability condition for the motor to be stable, your del value should be less than theta S. Then in case of motor and in case of generator, the condition are equal, are same. Okay, next is approximate analysis. The same thing we will going to do. Ignore the armature resistance, then ZS will become XS at an angle 90 degree, and write and replace the ZS theta S in the original equation here. So you will get input power, which is same as the generator case here, and Q input is VT upon XS, VT minus EF cos del. All right. So this is the reverse of your generator. See here. Just a second. Reverse of the generator. Okay. And this has to be happen because the direction of current has reverse is in opposite direction to that of the generator. All right. So this is minus Q out. But anyway, P develop is equal to again same, because you have ignored the armature resistance. So there will be no losses in the machine, and Q develop will not equal to Q in due to excess. Now the droop characteristic. What is droop? Means if a machine is operating at a certain frequency, let us say 50 Hertz, and if you are giving any load, if you are increasing the load in the synchronous machine, then the frequency will going to be reduced, because the speed is going to be reduced or decreased. All right. So by increasing the load, the speed will going to be decreased, and your frequency will going to be decreased, and the synchronous machine will losing its will lose its synchronism. And for the proper operation of the machine, all the synchronous, or you can say for the proper working of the synchronous machine, all the machine should have the same frequency. If any of the machine is having the frequency less than the frequency which other synchronous machine are operating, then the machine will going to be damaged. Am I clear? So here I have taken the two cases. This curve is known as the droop curve for the first machine, or you can say for the first generator, and this curve is for the second machine, which is known as second generator, and this is the second droop curve or the droop straight line curve, you can say. All right, so this is dash, this is D dash, and here we have B dash. Now in this, what we are need to find, we are need to find the unknown parameter, which is F, in which the both generator are operating. This is the first question that we can get, this unknown frequency F. The second part is that you are provided with a load, the total load for which these two generators are operating, that is PL, we can say. This is the total load, and this total load is supplied by the P1 and P2, means the generator 1 will give the power P1 and generator 2 will give the power P2. So the second question is, what will be the value of P1 or what will be the value of P2 such that it will deliver the total power PL for the case when it is not losing the synchronism, or at the situation where it is supposed to lose its synchronism. All right, so particularly at this frequency we are supposed to calculate. All right, now look at here. This is one triangle and this is another triangle, and all the triangle means these two triangle will have a same angle, isn't it? These two triangle will have OA B dash and OC dash D dash will have the same angle. So this is a similar type of triangle, you can say. So from here, can I say FNL minus F whole divided by, what is this power? Sorry, this power is P2. So this is tan theta, isn't it? Y by X. Now this is equal to, consider the bigger triangle. This is equal to, this is FNL2, sorry, this is FNL2. This is equal to FNL2 minus F full load 2 divided by this total power, which is P full load. Means this is the capacity of the generator 2. This is the capacity of the generator 2 which can give the full load power. All right, so this is the maximum value that the generator can give. So here, just a second, from here you will be having one equation, from here you will be having one equation, and from here you will be having the second equation. See this triangle, this bigger wala and one this smaller wala. These two triangle have the same angle, isn't it? So the smaller one, FNL1 minus F whole divided by this power, the smaller triangle P, this is equal to the bigger triangle FNL1 minus F full load 1 whole divided by this total power, which is PFL1. And here, from here you will get the two equation, means one equation here, one equation will be here, and we have three unknown. So definitely we will be requiring the three equation. So one equation we will get from here, second equation we will get from here, the third equation will be given in the question itself, that is the load power that the load is consuming. So the load power PL is equal to P1 plus P2. This is P1, this is P1. So find P1 from here and substitute in P1. Find P2, expression of P2 from here and substitute here. The only unknown parameter will be in this equation is F. So from there you can find the unknown frequency and you can find the P1 and P2 as well. Okay. So this is the power flow diagram of the alternator, and where the input is mechanical and output will be the electrical, isn't it? So this mechanical power input, when it goes into the into the rotor, it will come across the losses, which is friction and windage loss, and the core loss, which is oftenly known as no load rotational losses. And this is the air gap power, which is known as PAG, air gap power. I hope this is visible to you, or let me write here PAG, which is 3 times of IA cos psi, 3 times of 3 times of E into IA. This E is what? EF only. This E is EF into IA cos psi. Now, when this power will come across the stator, then when you subtract the field circuit VF IF power and the armature loss power and the stray load power to the internal power, you will get the output power, which is electrical, as 3 VT into IA into cos phi. Next, power flow diagram of synchronous motor. Just reverse the direction of the direction that we are getting in the alternator. You will get the power flow diagram for the alternator. For the motor. So in the motor, what is the input? Input will be your electrical and output will be your mechanical. So input is 3 VT into IA cos phi. Then this is the armature losses and the stray losses. This is internal air gap power, you can say, or internal power. And here we have a field circuit. Here we have a no load rotational loss, friction and windage loss. And after deducting all these losses, you will get the output power, which is torque into omega. Output power P out, this is equal to torque into omega S. Why omega S? Why not omega R? Because your rotor is rotating at a synchronous speed in the synchronous machine. Next is efficiency in the alternator. So efficiency will be equal to, again, output by input. So here in alternator, output is electrical. So this is 3 VT IA cos phi upon 3 VT IA cos phi plus losses. So which losses? These all losses. 3 IA square RA, straight load losses and no load rotational losses and field circuit loss. This 1, 2, 3, 4 and 5. These all losses you need to put here, and from there you will going to get the alternate power. Just a second. P naught by Pi into 100%. So for the alternator, we have a percentage efficiency. Now in case of motor, that is percentage efficiency of the motor, this is equal to 1 minus losses upon input. So input in case of motor is what? 3 VT into IA cos phi into 100%. I think we have written theta, na? Just a second, let me check. Also, okay, fine. We have written phi only. Next is salient pole synchronous machine. So in the salient pole synchronous machine, the rotor is not cylindrical. Rather, it is a rotor which is having this kind of construction, where this is referred as a north and this is referred as a south. So this is the salient type of rotor. What do you mean by cylindrical rotor? In the cylindrical rotor, the rotor will be cylindrical itself, or you can say the circular, isn't it? So in the salient pole machine, this will be your rotor construction. So in that, the power the power P will be equal to EF Vt by xd, EF Vt by xd sin del plus Vt square by 2, 1 by xq minus 1 by xd into sin 2 del, where del is the load angle. Now, the positive point or the advantage of the salient pole synchronous motor is that even if you are not giving the excitation to the machine, even if you are not giving the excitation to the machine, means if your IF value is 0 ampere, which implies EF to be 0 volt, then also we are having some amount of power which is known as reluctance power, because in the second term EF term is missing. In the second term the EF value is missing, the EF parameter is missing. So this is the reason why the salient pole machine is also termed as the more stable machine than the cylindrical type of machine, and we are getting some amount of extra power in terms of the reluctance. So your salient pole power is always greater than the power due to cylindrical type of machine. Okay, am I clear? So with this we have completed all the formulas that are important for the GATE question related to the subject electrical machine. Now let me take you to the things or the features that we offer for the student by the IMS GATE Academy. Alright, so this is our website. I request all of you to please visit at any time to our website. Definitely you will going to enjoy the courses that we are offering to the students. So this is our website. Alright, this is our toppers. So from here GATE ME, alright, please ignore this ME part. When you click this GATE ME tab, you will going to get the courses or you will get the branches, and with respect to branches you will be getting the courses. Alright. Next, this program the IMS GATE Academy has been offering to you, that is classroom program, hybrid classroom program, exclusively live online program, and self-learning program. In the classroom program, we are giving the 750 plus hours offline classes. Alright, no, we are not having live the online classes here. The whatever classes that we are conducting is totally offline, and these books we are giving to the students. Next is hybrid class. So in this, okay, please ignore this one. Okay, in the hybrid we are having online and offline and online session. All right, and the duration of the course is 750 plus hours. So in the offline 67% will be the offline session or the classes, and 33% will be your online classes. Am I clear? So this is the hybrid model in which the class will be conducted in the online and offline together, and these all books you are getting. Next is live online program, where you will get the 750 plus hours live online classes. Here you are not getting the physical interaction with the faculties. Means definitely you will see me, but I cannot see you. So that is why this is not the one-to-one interaction as we have for the offline classes, isn't it? So here you will get the total classes of 750 plus hours, and that will be online, and together with that you will be giving or providing with the this all features. Next is self-learning, means the 400 plus hours of the video lecture you will be going to get, and along with this booklets. All right. Next is the methodology that we are adopting for the student, or the suggestion that we are giving to the student to adopt this method, so that they can get a command over the subject. So the L means learn, P means practice, and T means test. So first the student will learn, then they will practice, and after that they will give a test. And definitely after this method, or if any one of the student are going to adopting this method, definitely he or she will going to get the good mark and the good rank in the exam. Let us move ahead. This is the test series that the GATE Academy of IMS GATE Academy that is offering, is the chapter test, subject basic level test, subject wise advanced level test, multi subject test, and full length mock test. So overall you are getting, I hope 125 plus test you are getting here. Okay, so next is GATE at zero fees, means at without investing any rupees you are getting these features: 100 plus hours of concept video, 12 chapter test, 6 subject test, and 6 past GATE paper. So for that you have to enroll at a free of cost, and after that you will be provided with these features. Next is student portal. So those students who has opted for the courses, they will get the e-lectures, that is the recorded lectures, live lectures you can also say, the PDF book of the theory book, as well as the practice booklet you can say, and the test series. All right. So in the e-book you will be provided with the theory booklet as well as the exercise book, and with the e-test you are provided with the test series for the respective subject and with the respective chapters. Now, student doubt solving portal. Whenever a student get stuck in any of the questions, or if he is facing any doubt related to the subject, which is known as technical doubt, then he or she can post here, and our ex-team and or the professional faculty will going to solve their doubt within a given amount of time. All right. So that doubt can be solved in a PDF manner, or in the JPG or JPEG manner. All right. So this is one of the advanced features of the IMS GATE Academy, and one of the most important, these features is very important of the IMS GATE Academy, or you can say this is the USP of the IMS GATE Academy, where the student are interacting one-to-one, which is known as one-to-one mentoring session, and one-to-many means one faculty and many student. So one-to-many mentoring session means we are mentoring or we are guiding to the student so that they can be able to achieve their goal without any restriction or without any difficulties. So this is a one kind of USP that IMS GATE Academy is having. So with this we have completed the electrical machines, all the formulas. So I request you to please like the session and also share the session with your friend, and subscribe to our YouTube channel, and also press the bell icon such that whatever session we are coming live in the upcoming events or in the upcoming days, you will going to be notified instantly. All right. So all the very best for your GATE exam and the future, and for your futures. Goodbye, and take a very good care of your health.